The Twin-Quasar Paradox happens because of a strange effect in space called gravitational lensing. This occurs when a massive object, like a galaxy, bends light from something behind it. In this case, the light comes from a quasar, which is a distant and extremely bright object powered by a black hole. The bending of light makes it look like there are two quasars when, in reality, there is only one. The paradox comes from the fact that these two images don't appear at the same time. Instead, one shows the quasar as it was in the past, and the other shows it at a different point in time. I'd love to invite you to share in the comments where you're listening from and what time it is. It's incredible to think about how we're all connected through these stories and ideas. If you enjoy these thought-provoking explorations, consider subscribing to Tired Thinker so we can keep bringing you reflective narratives. Now, settle in, get comfortable, and let your imagination drift as we delve into the mind-boggling paradoxes and mysteries. This effect challenges how we think about space, time, and observation. The first time scientists noticed this was in 1979 with a quasar known as Q0957 plus 561. It appeared twice in the sky, but detailed studies showed that the two images were actually of the same quasar. A massive galaxy sitting between Earth and the quasar had bent the light around it, splitting it into two separate paths. Since the light traveling along each path had to take different routes, one image arrived slightly later than the other. The delay between these images is not just a few seconds or minutes, but can be years. This means that when astronomers look at one image, they might be seeing the quasar in a different state than in the other image. To understand why this happens, picture a car driving through a city with multiple roads leading to the same destination. Some roads are direct, while others have detours or traffic lights that make the trip longer. Now imagine that instead of a car, it's light traveling through space, and instead of roads, it's gravitational fields bending that light. The quasar's light must take different paths because the galaxy in the middle warps space around it. The paths may be longer or shorter, which results in different travel times for the light that reaches Earth. This raises an interesting question. If the light from one path takes longer to reach us, does that mean we are looking at the past in one image and a different past in the other? The answer is yes. If a sudden burst of brightness occurs in the quasar, one image might show it happening, while the other image might not display it yet, because that light is still traveling to us. Astronomers use this delay to study quasars in a unique way. If they see a change in one image, they can predict when they will see the same change in the other image. This allows them to check their predictions about how light moves through space. The idea that light takes time to travel is not new. When we look at the sun, we are actually seeing it as it was about 8 minutes ago, because that's how long light takes to reach Earth. When we observe stars, we see them as they were years or even centuries ago. With quasars, the effect is even more extreme because they are billions of light years away. The Twin-Quasar Paradox shows that not only does light take time to reach us, but the same event can appear at different times, depending on the path the light takes. This also means that, in theory, if we had an extremely powerful telescope and could look at a quasar from multiple angles using different gravitational lenses, we could see multiple versions of its past at once. This is like having a time machine that lets us view the same event from different moments in history. Scientists use this effect to measure distances in the universe and to test theories about dark matter. The way the light bends tells them about the mass of the galaxy doing the bending, even if that mass includes invisible material like dark matter. One of the more surprising aspects of this paradox is that it isn't just a trick of light, it's a real demonstration of how gravity affects space itself. Albert Einstein predicted this in his general theory of relativity. According to his equations, massive objects curve the fabric of space, and light must follow those curves. He suggested that if a star passed behind the sun, its light would bend around the sun's gravity, making it look like the star had moved. This was later confirmed in 1919 during a solar eclipse. The Twin-Quasar Paradox is an even more dramatic example because the bending is so strong that it creates two separate images. The implications of this paradox go beyond just quasars. If light can be delayed by gravity, then signals we receive from deep space could also be arriving at different times. This has led to discussions about how time itself is experienced in different parts of the universe. If an astronaut could travel near a massive object and then return to Earth, they might have aged differently than people who stayed behind. This is similar to the well-known twin paradox in relativity, where one twin travels at high speed and returns younger than the twin who stayed on Earth. In the case of the Twin-Quasar Paradox, it is not people aging at different rates, but light itself revealing different moments in time. Another interesting aspect is that gravitational lensing doesn't always create just two images. In some cases, it produces four or even more. When light bends in complex ways, it can take multiple paths, creating several versions of the same object. This is called an Einstein cross. It happens when the lensing galaxy is perfectly aligned with the background quasar. Instead of two images, we see four distinct copies, each showing the quasar at slightly different times. Some astronomers have suggested that in rare cases, a gravitational lens could create an Einstein ring, where the background object appears as a full circle around the foreground galaxy. This happens when the alignment is perfect, and the light is bent equally in all directions. The same time delay effect applies, meaning different parts of the ring may actually show slightly different versions of the quasar's history. The Twin-Quasar Paradox also raises questions about what it means to observe something in space. If observation depends on when light arrives, then what we see at any moment is not necessarily what exists right now. The universe we observe is actually a collection of different times, spread out across space. Every star, planet, and galaxy appears to us as it was in the past, and the farther away we look, the deeper into history we go. In a way, this means that astronomers are not just studying space, but also time. Each observation is like looking through a window that reveals a different chapter of the universe's story. The Twin-Quasar Paradox is a reminder that time is not experienced in the same way everywhere. The light that reaches us has been shaped by gravity, delayed by distance, and altered by the structure of space itself. Because of gravitational lensing, scientists can also use quasars as cosmic tools. By studying how the light is bent, they can map the distribution of dark matter in the universe. Since dark matter doesn't emit light, it's nearly impossible to detect directly. However, its gravitational effects can be seen in how it warps the light of distant quasars. This method has provided some of the best evidence that dark matter exists. One might wonder if it's possible to use this effect to communicate across time. If light from the same event arrives at different times, could someone in the future use gravitational lensing to send messages to the past? So far, this remains purely theoretical. The delay between images is based on natural cosmic structures, not something that humans can control. But the idea adds to the mystery of how time and space interact. The Twin-Quasar Paradox is not just an interesting phenomenon, but also a crucial piece of evidence for how gravity and light behave on the largest scales. It confirms Einstein's predictions and helps scientists study the invisible parts of the universe. It also challenges how we think about time, showing that the past is not a single fixed moment, but something that can appear differently depending on where and how we look. The cosmological horizon paradox presents a problem in modern physics. It asks why different parts of the universe, which should never have been in contact, have nearly the same temperature. This issue arises when looking at the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. No matter where scientists look, the temperature of the CMB is about 2.73 Kelvin. The problem is that regions on opposite ends of the observable universe are too far apart for light or any signal to have traveled between them since the beginning of time. If these regions never exchanged energy, how did they reach the same temperature? The paradox comes from basic principles of physics. Heat spreads when objects exchange energy. If you put a hot and cold object together, they eventually reach the same temperature. The CMB suggests that the whole universe went through this process, yet some regions are so far apart that they should never have interacted. This contradicts what we expect based on the limits of how fast information can travel. Since no signal can travel faster than the speed of light, these distant parts of the universe should never have been able to communicate with each other. To understand why this is a problem, imagine a classroom. If students on opposite sides of the room are told to coordinate on an assignment but cannot speak or pass notes, they will likely come up with different results. Yet, if you check their papers and find identical answers, you would wonder how they managed to synchronize. The universe presents a similar mystery. Light, sound, or any form of energy could not have traveled between these regions, yet they appear to have coordinated their temperature. The problem becomes clearer when thinking about the speed of light and the age of the universe. The universe is about 13.8 billion years old. The speed of light, the fastest any signal can travel, limits how far information could have spread. This creates a boundary known as the cosmological horizon, beyond which regions of space have never interacted. If two regions have never interacted, they should have different temperatures. But observations show the opposite. To explain this, physicists introduced the idea of cosmic inflation. Inflation proposes that in the first tiny fraction of a second after the Big Bang, the universe expanded at a speed much faster than light. This rapid expansion smoothed out temperature differences before the regions became separated by vast distances. In this view, the entire observable universe started in a small, connected state where temperature differences could equalize before inflation stretched space. Inflation provides a neat solution, but it introduces new questions. What caused inflation? Why did it stop? No one has directly observed inflation, so it remains a theoretical fix rather than a proven answer. Another way to understand the problem is by looking at the concept of causality. Causality means that effects must have causes, and information can only spread at a limited rate. If one region of the universe affects another, there must have been time for signals to pass between them. But in the standard Big Bang model without inflation, these regions never had the chance to interact. They should have remained at different temperatures, just like separate pots of water heating up at different rates. Some alternative explanations have been proposed. One idea is that the speed of light might have been higher in the early universe, allowing temperature differences to smooth out faster. Another possibility is that the universe is shaped in a way that allows hidden connections between distant points, though this lacks strong evidence. Without inflation or another mechanism, the observed uniformity of the CMB remains unexplained. The paradox is important because it challenges our understanding of how the universe evolved. It suggests that either our model of the early universe is incomplete or that fundamental assumptions, like the constancy of the speed of light, might need revision. The paradox also connects to other mysteries, like dark energy and the ultimate fate of the universe. If inflation happened, it set the stage for everything that followed, including the expansion we see today. If inflation did not happen, we may need a different way to explain the uniformity of the cosmos. This problem is not just theoretical. Scientists use data from satellites like WMAP and Planck to measure the CMB with incredible precision. Every new observation confirms the near-perfect uniformity of the CMB, reinforcing the paradox. Yet without direct evidence of inflation, some physicists remain cautious. They look for ways to test inflation or propose alternative models that could resolve the paradox. The Cosmological Horizon Paradox highlights how little we know about the early universe. It forces scientists to consider ideas that challenge intuition, such as inflation, varying physical constants, or hidden connections in spacetime. The fact that the universe appears so uniform suggests that something beyond the standard Big Bang model must have shaped it. The search for answers continues, with new telescopes and experiments designed to probe the early moments of the universe in greater detail. The black hole firewall paradox suggests that our understanding of black holes is incomplete. It arises from a conflict between quantum mechanics and general relativity. General relativity describes black holes as regions of space where gravity is so strong that nothing, not even light, can escape. The boundary of this region is called the event horizon. According to Einstein's theory, if someone were to fall into a black hole, they would cross the event horizon without noticing anything unusual. From their perspective, they would continue falling toward the singularity at the center, where gravity becomes infinitely strong. Quantum mechanics tells a different story. In the 1970s, physicist Stephen Hawking discovered that black holes are not completely black. Instead, they emit radiation, now called Hawking radiation. This radiation comes from quantum effects near the event horizon. Over time, a black hole slowly loses mass and eventually evaporates. This creates a problem. If the black hole disappears, what happens to the information that fell into it? In quantum mechanics, information cannot be lost. Every physical process is reversible, meaning that if you know a system's final state, you should be able to work backward and determine its initial state. But if a black hole evaporates and leaves nothing behind, the information inside it would vanish. This is known as the black hole information paradox. Physicists tried to resolve this paradox in different ways. Some argued that information somehow escapes through Hawking radiation, even though Hawking's original calculations suggested otherwise. Others believed that information gets stored in a hidden way inside the black hole. But in 2012, a new idea emerged that created another problem. A group of physicists proposed that instead of smoothly passing through the event horizon, anything that falls into a black hole would hit a firewall, a searing wall of high-energy radiation that destroys everything on contact. This firewall would replace the smooth entry that general relativity predicts. If true, it would mean that the event horizon is not just an invisible boundary, but a physical surface with extreme energy. The idea of a firewall comes from a concept called entanglement. In quantum mechanics, particles can become entangled, meaning their states are linked no matter how far apart they are. Hawking radiation and the particles inside a black hole should be entangled. This entanglement preserves information. However, calculations show that if information escapes in the radiation, new particles being emitted must break their entanglement with older particles inside the black hole. This breaks a fundamental principle in quantum mechanics known as monogamy of entanglement, which states that a particle can't be fully entangled with two different systems at once. Breaking entanglement causes a release of energy, forming a firewall. This presents a serious problem. The firewall idea challenges the very foundation of general relativity. If an astronaut falls toward a black hole, Einstein's equations say they should feel nothing special as they cross the event horizon. But if firewalls exist, the astronaut would be instantly burned up. This would contradict the equivalence principle, a key idea in relativity that says free falling in gravity should feel the same as floating in empty space. The presence of a firewall would mean that gravity does something special at the event horizon, which goes against everything we know about how space and time work. The paradox has sparked intense debate. Some physicists argue that firewalls must exist to prevent the loss of information. Others believe that some unknown physics must resolve the contradiction. One approach is that the event horizon is not a real physical barrier, but an illusion created by quantum effects. Another idea is that space and time themselves are emergent properties that behave differently near black holes. Some theories suggest that information is not destroyed but scrambled and encoded in the event horizon itself, forming what's known as a holographic surface. One possible resolution comes from the concept of black hole complementarity. This idea suggests that the same event can be seen in different ways depending on the observer. To an outside observer, the astronaut never really crosses the event horizon. Instead, they appear to slow down and fade as they approach, with their information getting imprinted on the event horizon. But to the astronaut, they cross the event horizon and fall inward normally. This means no contradiction arises because different observers experience different realities. However, recent work suggests that even this idea might not fully solve the paradox. A related proposal is the idea that black holes may have soft hair. This means that instead of losing all information, black holes store a kind of faint imprint of everything that falls in. These imprints might be preserved in the Hawking radiation, allowing information to eventually escape. But this theory is still being developed, and no one has proven it to be correct. Another suggestion is that the entire paradox arises from an incorrect assumption about quantum gravity. Right now, we don't have a complete theory that unites quantum mechanics and general relativity. Some believe that once we discover such a theory, the apparent contradictions will disappear. String theory and loop quantum gravity are two leading candidates for this deeper theory, but neither has fully explained what happens at a black hole's event horizon. Firewalls challenge our basic understanding of space, time, and information. If they exist, they would overturn Einstein's ideas about black holes. If they don't, then something else must explain how information escapes. The paradox remains unsolved, leaving physicists searching for a deeper understanding of black holes and the nature of reality itself. The ultraviolet catastrophe was a major problem in physics that classical mechanics could not explain. It came from trying to understand how objects emit radiation when heated. Scientists expect that when an object is heated, it should give off light in a predictable way. But when they used classical physics to calculate this, they found something strange. The math predicted that as the frequency of light increased, the energy emitted would become infinite. This result made no sense because nothing in nature has infinite energy. To understand the problem, imagine heating a piece of metal. At first, it glows red. As it gets hotter, it turns orange, then yellow, and eventually white. If the heat keeps increasing, the metal should emit even more blue and violet light. But classical physics suggested something different. The equations said the metal should keep producing more and more ultraviolet light, and eventually X-rays and gamma rays. It predicted that the total energy would be infinite because high-frequency waves should contribute endless energy. This was clearly wrong because everyday experience shows that objects don't behave this way. A hot object doesn't suddenly burst with infinite energy. The issue came from the way classical physics treated light. Scientists thought of light as a wave, like ripples in water. According to wave theory, energy could be spread out in any way. Classical physics assumed that at every possible frequency, an object could emit radiation. If that were true, higher frequencies, like ultraviolet light, would have more energy than lower frequencies, like red or yellow light. Since there was no limit on how much energy an object could give off at high frequencies, the total energy added up to infinity. Physicists tried different ways to fix the problem, but none of them worked. The theory of electromagnetism, developed by James Clerk Maxwell, described light very well in other situations. It explained how light waves move and interact with electric and magnetic fields. But when it came to blackbody radiation, it failed completely. The problem became so serious that it forced physicists to rethink how energy works at a fundamental level. The solution came from Max Planck in 1900. Instead of treating light as a continuous wave, he proposed something new. He suggested that light comes in small, discrete packets called quanta. This idea was radical because, at the time, most scientists believed energy could be divided into infinitely small amounts. Planck's idea meant that an object could only emit energy in fixed amounts, not continuously. These packets, later called photons, depended on the frequency of light. Higher frequency light had larger packets, while lower frequency light had smaller packets. To see why this solved the problem, imagine throwing coins into a vending machine. If you could only put in whole coins, you wouldn't be able to insert half a coin or a quarter of a coin. Planck's theory worked in a similar way. An object couldn't emit tiny bits of energy continuously. Instead, it could only emit full packets of energy, with a minimum size determined by its frequency. At high frequencies, the packets became too large, making it harder for an object to emit radiation. This prevented infinite energy buildup and solved the ultraviolet catastrophe. Planck introduced a new constant to describe the size of these energy packets. This number, now called Planck's constant, turned out to be one of the most important values in physics. It showed that energy is not continuous but comes in small steps. This idea marked the beginning of quantum mechanics. At first, even Planck didn't fully believe in his own idea. He introduced quanta as a mathematical trick to make the equations work. But soon, others realized that this was more than just a clever fix. In 1905, Albert Einstein used Planck's idea to explain the photoelectric effect, another problem classical physics couldn't solve. He showed that light behaves not just as a wave, but also as a particle. This discovery led to the idea that energy and matter follow quantum rules. The ultraviolet catastrophe was one of the first signs that classical physics was incomplete. It showed that light and energy behave in ways that older theories could not explain. Planck's quantum theory opened the door to a new understanding of nature. Over time, this led to quantum mechanics, which describes how particles and energy behave at small scales. The problem of infinite energy disappeared because nature does not allow continuous energy emission. Instead, energy is quantized, meaning it comes in fixed amounts. One way to visualize this is by thinking of a staircase. In classical physics, energy was thought to be like a smooth ramp, where you could step anywhere. But quantum mechanics showed that energy is more like a staircase, where you can only stand on specific steps. This explains why high-frequency radiation does not lead to infinite energy. The steps get bigger as the frequency increases, making it harder for objects to emit very high-frequency light. Planck's work led to many other discoveries in quantum mechanics. Scientists later found that atoms and electrons also follow quantum rules. Quantum theory helped explain chemical reactions, the behavior of materials, and even the structure of the universe. The ultraviolet catastrophe was just the beginning of a much larger revolution in physics. Another example of how quantum mechanics fixed classical physics comes from lasers. Lasers work by using specific energy levels in atoms to produce light. Classical physics would predict that atoms could release energy in any amount, making lasers impossible. But quantum mechanics showed that atoms emit light in precise steps, which is why lasers can create focused, powerful beams. The ultraviolet catastrophe also played a role in understanding the heat given off by stars. The sun emits light in a spectrum that peaks in the visible range. If classical physics were correct, the sun would radiate most of its energy in the ultraviolet range, making it far too bright and dangerous. But because of Planck's discovery, we know that stars follow quantum rules when emitting energy. This explains why sunlight is spread across different wavelengths instead of being dominated by ultraviolet radiation. Planck's idea also helped scientists develop modern electronics. Devices like LEDs and solar panels rely on quantum principles to work. Without the discovery of energy quantization, many modern technologies would not exist. The ultraviolet catastrophe was more than just a problem in physics. It was the key that unlocked a new way of understanding nature. At the time, the idea of quantized energy seemed strange. Many physicists resisted it because it went against everything they had learned. Classical physics worked well for everyday objects, so it was hard to believe that the laws of nature changed at small scales. But as more experiments confirmed Planck's theory, scientists had to accept that quantum mechanics was real. Even though the ultraviolet catastrophe seemed like a small issue at first, it turned out to be a major turning point in physics. It forced scientists to abandon old ideas and create new ones. The problem of infinite energy disappeared because nature does not allow continuous energy emission. Instead, energy is quantized, meaning it comes in fixed amounts. This discovery changed the way we understand light, heat, and matter, leading to the development of quantum mechanics. The Double-Slit Paradox is one of the most famous puzzles in quantum mechanics. It challenges the way we understand reality. When scientists send particles, like electrons or photons, through two narrow slits in a barrier, the results defy logic. If no one measures which slit each particle goes through, they create an interference pattern on a screen behind the barrier. This pattern looks like waves interfering with each other, even though the particles move one at a time. But when scientists place a detector to check which slit each particle passes through, the pattern changes. Instead of spreading out like a wave, the particles behave like small bullets, forming two distinct clusters behind the slits. This experiment suggests that particles act differently depending on whether they are observed. If no one watches, they behave like waves. If someone measures them, they act like particles. This behavior raises deep questions about reality. Does the particle know it is being watched? Does measurement change its nature? The experiment has puzzled scientists for more than a century. Imagine a baseball player practicing alone in a stadium. If you walk in and see the balls scattered across the field, you assume they followed predictable paths. But what if, instead, you see a strange pattern of overlapping rings? And what if the moment you look closer, the balls snap into a normal arrangement? That is similar to what happens in the double-slit experiment. The particles seem to exist in multiple places at once, spreading out like ripples in water. But the instant someone checks their path, they choose a single location. The mystery deepens when scientists send particles through the slits one at a time. You might expect them to form two piles behind the slits, since each particle moves alone. But if no one measures them, the particles build an interference pattern as if they interfere with themselves. It is as if each particle travels through both slits at once. This idea clashes with common sense. In everyday life, objects do not exist in two places at the same time. Scientists have tried different methods to understand this effect. Some have used detectors to measure which slit the particle passes through. Each time they do this, the interference pattern disappears. This suggests that the act of measurement forces the particle to choose a single path. But what if the detector is present but does not record the data? Even then, the interference pattern vanishes. This means that merely having the possibility of knowing the path is enough to change the outcome. Some scientists explain this effect using the idea of wave function collapse. In quantum mechanics, particles do not have fixed locations until someone measures them. Instead, they exist as a wave of possibilities, called a wave function. This wave spreads out, covering different positions at once. When someone measures the particle, the wave collapses, forcing it into a definite spot. But why does measurement cause this collapse? No one knows for sure. One explanation comes from the Copenhagen interpretation, named after the city where physicist Niels Bohr worked. This idea says that quantum particles do not have definite properties until measured. Until then, they exist in a state of probability. Measuring them forces them into a particular state. According to this view, reality itself is not fixed until observed. Another explanation is the many worlds interpretation. This idea suggests that measurement does not collapse the wave function. Instead, all possible outcomes happen, but in different parallel universes. If a particle goes through the left slit in one universe, it goes through the right slit in another. We only see one result because we exist in one of these universes. This idea removes the need for wave function collapse, but it raises new questions. If every possibility happens, why do we experience only one reality? Some physicists have tested whether the interference pattern still forms if they delay the measurement. They set up a version of the experiment where they decide whether to measure the particle after it has passed through the slits, but before it hits the screen. Strangely, even in this setup, the results change based on whether a measurement occurs. It is as if the particle's past behavior depends on future choices. This concept, called the delayed choice experiment, challenges our understanding of cause and effect. Another strange version of the experiment involves entangled particles. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. Scientists have used entangled pairs in the double-slit experiment. The results suggest that the behavior of one particle depends on how its entangled twin is measured. This effect happens instantly, even if the particles are light years apart. Some scientists think this could mean that information travels faster than light. Others believe it shows that reality is fundamentally interconnected. The double-slit experiment has implications beyond physics. It suggests that reality does not exist in a definite state until it is observed. This raises questions about the role of consciousness in shaping the physical world. Some thinkers argue that observation creates reality. Others say that quantum mechanics only describes probabilities, not definite outcomes. Despite its mysteries, the double-slit experiment has practical applications. Quantum mechanics, the theory that explains this paradox, has led to technologies like lasers, transistors, and quantum computers. Engineers use quantum principles to create secure communication systems. Scientists are also exploring ways to harness quantum behavior for advanced computing. Researchers continue to test and refine their understanding of quantum mechanics. Some hope that new experiments will reveal hidden variables that determine a particle's behavior. Others believe that quantum mechanics is complete but misunderstood. The paradox remains a fundamental mystery in physics. The double-slit experiment challenges the idea that the world exists independently of observation. It suggests that at the smallest scales, reality behaves in ways that seem impossible. Whether reality depends on the observer or not remains an open question. Scientists continue to explore this puzzle, searching for a deeper understanding of the universe. The quantum Zeno effect describes a strange phenomenon in quantum mechanics. When a quantum system is measured repeatedly, it stops changing. This effect seems counterintuitive because we expect things to evolve naturally over time. But in the quantum world, frequent observation can freeze a system's state. To understand this, imagine a radioactive atom that is expected to decay. If left alone, it will break down into smaller particles after a certain period. But if someone continuously checks on the atom, it may never decay. The act of measurement itself disrupts the natural process, holding the atom in its original state. This is different from classical physics, where observing something does not usually change its behavior. A simple way to think about this is by imagining a classroom experiment with a student taking a test. Normally, a student writes answers at a steady pace, but if a teacher stands over their shoulder and watches closely, the student may freeze, hesitate, or even stop writing. The constant observation affects their behavior. In quantum mechanics, something similar happens. The frequent measurement interrupts the normal progression of a system. Quantum mechanics operates on probabilities. A particle does not have a definite state until it is measured. Instead, it exists in a superposition, meaning it can be in multiple states at once. When measured, the particle chooses a state. If measurements happen too often, the particle keeps resetting to its initial state instead of evolving naturally. To put this into numbers, imagine a system where a quantum state changes over time. The probability of transitioning to a new state depends on time passing without measurement. If measured occasionally, the system has time to evolve before being observed. But if measured constantly, the transition probability keeps getting reset, making change impossible. This idea was first proposed in the 1970s by physicists studying how quantum states behave over time. They found that continuous observation slows or even halts the evolution of a quantum system. This result was surprising because it suggested that the mere act of looking at a system could control its behavior. A famous experiment that demonstrates the quantum Zeno effect involves unstable particles. Physicists prepared a system where an excited atom was expected to decay over time. When they measured it at normal intervals, the atom decayed as expected, but when they increased the frequency of measurements, the decay process slowed. When measured rapidly enough, the atom remained in its excited state indefinitely. The name Zeno comes from an ancient Greek philosopher, Zeno of Allais, who proposed paradoxes about motion and time. One of his famous paradoxes suggests that a runner can never reach the finish line because they must always cover half the remaining distance first. The quantum Zeno effect is similar because continuous measurement prevents a quantum system from completing its natural change. Another way to think about this is to imagine flipping a coin. If the coin is flipped and left alone, it will land on heads or tails. But if someone interrupts the coin in midair, stopping the flip each time before it lands, it will never settle into a final result. The quantum Zeno effect works the same way. The repeated measurement stops the system from progressing to its expected outcome. The effect has been tested in laboratory conditions using lasers, superconducting circuits, and ultra-cold atoms. Experiments confirm that when a quantum system is measured frequently enough, its evolution slows dramatically or even stops. This has implications for quantum computing, where fragile quantum states need to be maintained for calculations to succeed. If measurements are not handled carefully, they can prevent the quantum computer from working properly. This phenomenon also connects to a broader idea in quantum mechanics called wave function collapse. The wave function is a mathematical description of a quantum system that includes all possible states it can be in. When a measurement occurs, the wave function collapses, forcing the system into one specific state. If measurements happen repeatedly, the wave function keeps collapsing back to the same state, preventing the system from evolving. To see how this applies in a real-world setting, consider an electron in an atom. Normally, electrons transition between energy levels over time. If left alone, an electron will eventually jump to a lower energy state, releasing light in the process. But if the electron is observed repeatedly, it may never jump. The repeated interaction forces it to stay in its original energy level. One application of the quantum Zeno effect is in quantum error correction. Quantum computers rely on delicate quantum states to perform calculations. However, these states can be disrupted by outside influences, leading to errors. By using controlled measurements, scientists can prevent certain unwanted transitions, keeping the quantum state stable. The effect also plays a role in atomic clocks, which use the vibrations of atoms to measure time with extreme precision. In some designs, controlled measurement techniques help maintain the stability of atomic states, improving accuracy. Some researchers explore whether the quantum Zeno effect has connections to consciousness and perception. Since the act of observation influences quantum behavior, some speculate about whether consciousness itself plays a role in shaping reality. While this idea remains controversial, it highlights the deep implications of measurement in quantum mechanics. Experiments have also shown the opposite effect, known as the anti-Zeno effect. In some cases, frequent measurement can speed up transitions instead of slowing them down. The difference depends on how the measurements interact with the quantum system. This duality suggests that observation does not just passively reveal information, but actively influences what happens. Understanding the quantum Zeno effect helps clarify one of the core mysteries of quantum mechanics, the relationship between measurement and reality. It demonstrates that observing a system is not a neutral act, but an intervention that changes how the system behaves. This challenges classical intuition, where measurement is simply a way to gather information without affecting the thing being measured. This effect has no direct parallel in everyday life. In classical physics, measuring something does not prevent it from moving or evolving. But in the quantum world, where probability and uncertainty dominate, measurement reshapes reality itself. The quantum Zeno effect is one of many strange results that highlight the unique nature of the quantum realm. The quantum suicide paradox is a thought experiment based on quantum mechanics and the many worlds interpretation. It describes a situation where an observer's survival depends on quantum events. In one version of reality, the observer dies. In another, they continue living. This experiment raises questions about the nature of probability, consciousness, and reality itself. To understand the paradox, it helps to first look at Schrödinger's cat experiment. A cat is placed inside a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter detects it, breaking the vial and killing the cat. If the atom does not decay, the cat stays alive. Before opening the box, the cat is both dead and alive, existing in a superposition of states. When someone looks inside, the wave function collapses and the cat becomes either dead or alive. The quantum suicide paradox takes this idea further. Instead of a cat, imagine a person in a setup where their survival depends on a quantum event. The experiment involves a gun connected to a quantum measurement device. The device measures the spin of a particle. If the spin is up, the gun does not fire. If the spin is down, the gun fires, killing the person instantly. Each time the device makes a measurement, it randomly picks between these two outcomes. If the many worlds interpretation is correct, reality splits every time a quantum event happens. In one world, the particle's spin is up and the person survives. In another, the spin is down and they die. Every time the experiment runs, reality branches. From an outside observer's point of view, half the time the person dies. But from the person's perspective, they always find themselves in the branch where they survive. This means they never experience their own death. This idea challenges how people think about probability. Normally, if something has a 50% chance of happening, there is an equal likelihood of either outcome. But in this experiment, the person always finds themselves in a reality where they live. From their perspective, it feels like they are immortal. This is why some call it the quantum immortality paradox. To see how strange this is, imagine a scientist setting up the experiment with themselves as the subject. They start the machine and pull the trigger. In one world, the gun fires and they die instantly. In another, the gun does not fire and they continue living. They repeat the process. Each time, they only experience the version of reality where they survive. To them, it seems as though they have escaped death every time. From an outside perspective, however, there are many realities where they are dead. This paradox raises questions about how consciousness works. If reality splits every time a quantum event occurs, what does that mean for the person experiencing it? Does their consciousness only follow the paths where they survive? If so, does that mean death is never experienced directly? The thought experiment suggests that from a first-person perspective, a person might never experience the moment of their own death. Instead, they only continue in the branches where they remain alive. This concept has implications beyond thought experiments. It challenges traditional ideas about probability and observation in quantum mechanics. The many worlds interpretation suggests that all possible outcomes happen, but we only observe one. Most physicists do not believe in quantum immortality because it implies a strange version of reality where people never die in their own experience. It also does not match what we see in real life. People age, suffer accidents, and eventually die. If quantum immortality were real, one might expect to see evidence of people living forever in their own experience, which we do not. Despite this, the paradox remains an interesting way to explore the nature of reality. If true, it would mean that death is only a perspective shift, rather than an absolute event. Each individual would always experience a version of the world where they survive, no matter how unlikely. This idea has similarities to the anthropic principle, which suggests that we only observe a universe capable of supporting life because otherwise we would not be here to observe it. The paradox also connects to debates about the nature of consciousness. If every possible outcome occurs, what determines which version of reality a person experiences? If someone survives each time, does that mean their consciousness follows a specific path through reality? This raises questions about whether consciousness is tied to physical processes or if it exists independently in some way. One way to test the many worlds interpretation would be to look for evidence of quantum branching. Some physicists have proposed experiments that could detect interference between parallel realities. So far, no experiment has proven or disproven the existence of other quantum worlds. The many worlds interpretation remains one of several competing theories in quantum mechanics, alongside the Copenhagen interpretation, which suggests that wave functions collapse into a single outcome when observed. If the many worlds interpretation is correct, it means reality is much larger than what we perceive. Every moment, countless versions of reality branch off. Each decision, each random event, creates new versions of the universe. The quantum suicide paradox takes this idea to an extreme, suggesting that individuals only ever experience the paths where they survive. This conflicts with everyday experience, where people clearly die and there is no evidence of infinite survival. Even though the experiment is purely theoretical, it forces people to reconsider how reality works. Quantum mechanics is full of strange ideas, and the nature of measurement and observation remains an open question. The paradox does not prove quantum immortality, but it highlights the odd implications of quantum theory and the many worlds interpretation. The Klein Paradox describes a strange situation in quantum mechanics. In classical physics, a particle cannot pass through an infinitely high barrier. If the energy required to cross the barrier is greater than the particle's own energy, the particle should simply bounce back. But in relativistic quantum mechanics, something different happens. A particle approaching a very high potential barrier does not always reflect. Instead, under certain conditions, it can tunnel through as if the barrier is not there. Even more strangely, when the barrier is high enough, more particles seem to appear on the other side than were originally sent in. This behavior challenges common intuition and highlights the differences between classical physics and quantum mechanics. To see why this is surprising, imagine throwing a ball at a solid wall. If the wall is tall enough, the ball will never make it to the other side. It will hit the wall and bounce back. The same should apply to particles in quantum mechanics, except for a well-known phenomenon called quantum tunneling. Even if a barrier is too high for a particle to cross, quantum mechanics allows a small probability that the particle will appear on the other side. This happens in normal quantum mechanics with finite barriers. But the Klein paradox goes further. When a barrier is very high, so high that it should be impossible to cross, a surprising thing happens. Instead of fewer particles getting through, more particles appear on the other side. The paradox comes from solutions to the Dirac equation, which describes the behavior of particles like electrons that move close to the speed of light. In non-relativistic quantum mechanics, the Schrödinger equation describes how particles behave, including how they reflect from and tunnel through barriers. But the Schrödinger equation does not take into account relativity. When scientists apply the rules of relativity, they use the Dirac equation instead. The problem is that when a very high potential barrier is added to the equation, unexpected solutions appear. Instead of stopping all particles, the barrier creates new particles. One way to understand this is by looking at energy levels. In normal quantum mechanics, a particle's energy determines whether it can pass a barrier. If its energy is lower than the barrier, it has almost no chance of getting through, except by weak quantum tunneling. But in relativistic quantum mechanics, there is something called negative energy states. These are states that should not exist in classical physics. In everyday experience, energy is always positive. Things either have energy or they have none. But in the Dirac equation, there are solutions where particles seem to have negative energy. Physicists interpret these negative energy states using the idea of particle-antiparticle pairs. In quantum field theory, empty space is not actually empty. It is full of virtual particles that can appear and disappear. When a particle encounters a very high barrier, instead of simply reflecting, it can create an antiparticle. This new particle then appears on the other side of the barrier. This process is related to pair production, where energy can create a particle and its corresponding antiparticle from nothing. In the case of the Klein paradox, when the barrier is high enough, the energy needed to create new particles becomes available, and instead of just a single particle passing through, new particles appear. An example of this in the real world is the behavior of electrons near strong electric fields. When an electron approaches a region with an extremely strong electric field, such as near a highly charged nucleus, the field can cause electron-positron pairs to appear. Instead of just one electron interacting with the field, a new positron can emerge as well. This effect is similar to what happens in the Klein paradox. This paradox also raises questions about the meaning of a barrier. In classical physics, a barrier is just an obstacle that prevents something from passing. In quantum mechanics, a barrier is something that affects the wave function of a particle. In relativistic quantum mechanics, a barrier can sometimes act as a source of energy rather than just a simple obstacle. When the energy conditions are right, the barrier does not just stop particles, it creates new ones. The Klein paradox has practical implications in fields such as high-energy physics and semiconductor technology. In semiconductors, electrons sometimes behave in ways similar to relativistic particles, even though they are not moving at the speed of light. Understanding how electrons interact with barriers helps in designing electronic devices that rely on quantum effects, such as transistors and diodes. In particle physics, the paradox helps explain how particles behave in extreme conditions, such as inside powerful accelerators or near black holes, where energy barriers can be very high. Another way to think about the Klein paradox is by considering what happens when energy conservation meets quantum mechanics. In classical physics, energy is always conserved in an obvious way. Whatever energy goes into a system comes out in some form. In quantum mechanics, energy conservation still holds, but it can take unexpected forms. When a particle encounters a barrier that is too high to cross, instead of simply reflecting, it can interact with the vacuum and pull new particles into existence. This is not a violation of energy conservation, but a result of how energy behaves in quantum field theory. The Klein paradox also connects to the idea of vacuum polarization. In strong fields, empty space itself can behave like a medium that changes the way particles move. When an electron approaches a barrier, it does not simply see a hard wall. It interacts with a complex structure of virtual particles and fields. This interaction can lead to effects that would seem impossible in a simple classical picture. Some researchers have explored how the Klein paradox could be tested in laboratory conditions. One possible test involves using graphene, a material where electrons behave like relativistic particles. In graphene, electrons move in a way that follows equations similar to the Dirac equation. If a high enough potential barrier is created in graphene, electrons might show effects similar to the Klein paradox. Instead of being blocked by the barrier, they could pass through more easily under certain conditions. Experiments with graphene have already shown unusual tunneling behavior that supports some predictions of relativistic quantum mechanics. The paradox also has implications for the study of black holes. Near the event horizon of a black hole, the gravitational field is so strong that it can create particle-antiparticle pairs from empty space. This process, known as Hawking radiation, is similar in some ways to what happens in the Klein paradox. Just as a strong potential barrier can create new particles, a strong gravitational field can pull particles out of the vacuum. Understanding these effects helps physicists explore the behavior of matter and energy in extreme environments. The Klein paradox challenges the idea that barriers always stop particles. In the world of relativistic quantum mechanics, barriers can sometimes act as sources of new particles rather than just obstacles. This idea is important for understanding many areas of physics, from the behavior of electrons in materials to the way particles emerge in high-energy environments. While classical physics suggests that a high enough barrier should completely block particles, quantum mechanics reveals a different picture, where energy and the vacuum itself play a role in what happens when a particle encounters an obstacle. Renormalization is a process in quantum field theory that removes infinite quantities from calculations to make predictions match reality. The problem begins when physicists try to calculate the behavior of particles at very small scales. The equations they use sometimes give results that include infinite values, which do not make sense in the real world. To fix this, they use a technique called renormalization, which replaces the infinities with finite, measurable values. This process works, but it raises a deeper question. Why do the infinities appear in the first place? And does renormalization truly explain them? Or does it just hide them? Imagine trying to measure the energy of an electron in an electric field. If you follow the equations of quantum electrodynamics, the theory that describes how light and matter interact, you quickly run into a problem. The energy of the electron appears to be infinite. That makes no sense because electrons have finite energy. Physicists realize that this happens because their equations assume that particles can interact at infinitely small distances, which leads to infinite energy. But in the real world, distances cannot shrink to absolute zero, and this suggests that the infinities in the equations are artifacts of the way the theory is set up, rather than something real. To deal with this, physicists use renormalization. The idea is simple. Instead of allowing infinite energy values, they introduce a cutoff, a smallest possible scale where the theory still makes sense. Then, they adjust the equations so that all measurable quantities, like an electron's charge or mass, remain finite. This process works and allows quantum field theory to make extremely accurate predictions. For example, quantum electrodynamics predicts the magnetic moment of the electron with astonishing precision, matching experimental results to many decimal places. A useful way to think about renormalization is by comparing it to how people deal with rounding errors in real-world calculations. Suppose you are working on a large-scale map of a country and need to calculate distances between cities. If you try to measure every tiny bump and curve in every road, your calculations become impossible. Instead, you ignore details smaller than a certain scale and round off measurements to a useful level of precision. This doesn't mean the bumps and curves don't exist. It just means that they don't affect the final result in a way that matters for your purposes. Renormalization works similarly. Physicists set a limit on the smallest scales they consider, adjust their equations to cancel out infinities, and focus on results that can be tested in experiments. This allows quantum field theories to work, but it also raises an uncomfortable question. If infinities appear in the theory and are only removed through this process, does that mean the theory itself is incomplete? One of the most famous cases of renormalization is in quantum electrodynamics, or or QED. When Richard Feynman, Julian Schwinger, and Sin-Ichiro Tomonaga developed QED in the 1940s, they encountered infinities in their calculations. By using renormalization, they found a way to cancel out these infinities and extract meaningful predictions. Their approach was incredibly successful and helped establish quantum field theory as the foundation of modern physics. However, some physicists, including Feynman himself, found renormalization unsettling. He once described it as a dippy process because it seemed like a mathematical trick rather than a deep explanation of nature. The paradox of renormalization becomes clearer when looking at the strong nuclear force which holds atomic nuclei together. The theory that describes this force, quantum chromodynamics, or QCD, is also a quantum field theory, but it behaves differently from QED. In QE, the strength of interactions between particles decreases as they get closer together. This allows renormalization to work smoothly. But in QCD, the interaction strength increases at small distances, leading to a different type of problem. At very high energies, the theory becomes increasingly difficult to handle, and the usual renormalization techniques do not work as well. This suggests that QCD, and perhaps other quantum field theories, may only be approximations of a deeper theory that we do not yet understand. Another place where renormalization becomes tricky is in quantum gravity. Unlike the other forces of nature, gravity is not yet fully explained by quantum field theory. Attempts to quantize gravity using the same methods as QED and QCD run into severe problems with infinities. In standard quantum field theories, renormalization helps remove infinities by adjusting certain constants, like charge and mass. But in quantum gravity, the number of infinities is too large, and renormalization fails. This suggests that gravity requires a different approach, possibly through a theory like string theory, which replaces point-like particles with tiny, vibrating strings. The need for renormalization raises questions about whether quantum field theory is the ultimate description of nature or just a useful approximation. Some physicists suspect that the infinities arise because the theory assumes that space and time are continuous, stretching infinitely in all directions. If space and time have a smallest possible unit, a fundamental graininess at incredibly small scales, then the infinities might disappear naturally. This idea appears in some theories of quantum gravity, where space and time are thought to emerge from more fundamental building blocks. Another way to think about renormalization is by considering how people understand physical laws at different scales. Imagine studying the motion of water in a river. At a large scale, you can describe the flow using simple equations based on averages. But if you zoom in and examine individual water molecules, you need a completely different theory based on atomic interactions. The laws that work at one scale do not necessarily apply at another. Renormalization suggests that the same might be true for fundamental physics, that quantum field theory works well at certain scales, but a deeper theory may be needed to explain what happens at the very smallest distances. One of the biggest open questions in physics is whether the need for renormalization points to a flaw in quantum field theory or simply reflects the way nature works. Some physicists believe that the infinities are a sign that our theories are incomplete. Others argue that renormalization is just a practical tool, and there is no deeper mystery behind it. What is clear is that renormalization allows quantum field theory to make some of the most accurate predictions in all of science, even if its mathematical foundations remain somewhat mysterious. Physicists continue to explore these questions, looking for clues in experiments and in new theoretical models. The search for a theory of everything, which would unify all the fundamental forces, may ultimately reveal whether renormalization is a temporary fix or a key feature of the universe. Until then, renormalization remains one of the most effective yet puzzling tools in modern physics, a method that removes infinities while leaving behind deep questions about the true nature of reality. The universe is expanding, and not only that, but the expansion is also speeding up. This fact goes against the expectation that gravity should pull everything together and slow the expansion down. If galaxies are moving apart, gravity should act like a brake, resisting the motion. Instead, astronomers have discovered that the universe is stretching apart at an increasing rate. This discovery was unexpected and raised one of the biggest questions in modern physics. In the early 20th century, scientists thought the universe was static. Many believed it had always existed in a steady, unchanging state. Then, in 1929, Edwin Hubble observed that distant galaxies were moving away from us. The farther away they were, the faster they seemed to be receding. This discovery showed that space itself was expanding. If the universe is growing, then it must have been smaller in the past. This idea led to the Big Bang theory, which describes how the universe started from a tiny, dense state and has been expanding ever since. For a long time, scientists assumed that expansion would slow down over time. Gravity is an attractive force, pulling objects toward one another. Even though galaxies are moving apart, their mutual gravitational pull should be working against the expansion, making it gradually decrease. It was widely believed that the universe might eventually stop expanding and collapse back on itself in a big crunch, or that expansion would slow forever, but never completely stop. This idea changed in the late 1990s when two teams of astronomers studied distant supernovae. Supernovae are exploding stars that shine with predictable brightness, making them useful as cosmic measuring tools. By comparing their observed brightness to their distance, scientists can determine how fast the universe was expanding in the past. The results were shocking. Instead of slowing down, the expansion of the universe was speeding up. Something was pushing galaxies apart faster than before. This discovery challenged everything scientists thought they knew about the cosmos. If gravity is supposed to slow expansion, what could be causing it to speed up? The best explanation so far is that an unknown form of energy, called dark energy, is responsible. Unlike normal matter, which clumps together due to gravity, dark energy seems to work in the opposite way, pushing things apart. It acts like an invisible force accelerating the stretching of space. Dark energy does not behave like ordinary matter or radiation. It does not form structures like stars or planets, and it does not seem to interact with normal particles. Its only noticeable effect is that it accelerates the expansion of the universe. Current observations suggest that dark energy makes up about 70% of the total energy in the cosmos. Despite this, scientists do not know what it is or why it exists. One way to think about dark energy is to compare it to an inflating balloon. Imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart, just like galaxies in space. If the inflation speeds up over time, the dots will separate faster and faster. In the universe, space itself is expanding, carrying galaxies with it. The acceleration suggests that some unknown force is acting like a constant outward push. One possible explanation for dark energy comes from an idea proposed by Albert Einstein in 1917. When he first developed his equations for general relativity, he included a term called the cosmological constant. This term acted as a repulsive force that balanced gravity, keeping the universe from collapsing. Later, when astronomers discovered that the universe was expanding, Einstein abandoned the idea, calling it his biggest blunder. But when dark energy was discovered, scientists reconsidered his original concept. The cosmological constant might be real after all, explaining why expansion is accelerating. Another idea is that dark energy could be linked to a property of space itself. In quantum mechanics, empty space is never truly empty. Instead, it constantly produces and destroys tiny particles. These fluctuations could create a form of energy that acts as dark energy. However, calculations for this effect give results that are vastly different from what is observed, making this explanation uncertain. There is also the possibility that scientists do not fully understand gravity. Einstein's theory of general relativity explains how gravity works on large scales, but if a deeper theory of gravity exists, it might explain why the universe expands the way it does. Some alternative models suggest that gravity behaves differently at cosmic distances, producing effects similar to dark energy. Despite these uncertainties, observations strongly support the idea that the universe's expansion is accelerating. Scientists have measured the effect using multiple methods, including studies of the cosmic microwave background, which is the faint radiation left over from the Big Bang. These measurements confirm that something is pushing space apart, though its exact nature remains unknown. The discovery of dark energy has raised new questions about the future of the universe. If the expansion continues to accelerate, galaxies will drift farther apart until they become unreachable. In the distant future, observers in our galaxy may no longer see other galaxies, as the universe will have expanded so much that their light will never reach us. Some models even suggest that dark energy could grow stronger over time, eventually tearing apart galaxies, stars, and even atoms in an event called the Big Rip. The expanding universe paradox remains one of the biggest mysteries in modern science. The fact that space is stretching apart at an increasing rate contradicts the expectation that gravity should slow the process. While dark energy offers a possible explanation, its true nature is still unknown. Scientists continue to study the universe, searching for clues that might reveal what is driving its accelerated expansion. Wigner's friend paradox presents a strange idea in quantum mechanics. Two observers can see different realities, and both can be correct. This idea challenges how we think about objective truth. It builds on the famous Schrödinger's cat thought experiment, but takes it a step further by adding an observer watching another observer. To understand the paradox, start with the basics of quantum mechanics. In this theory, particles exist in multiple states at once. This idea is called superposition. A classic example is a quantum particle that can spin in two directions at the same time. But when someone measures the particle, it settles into one definite state. The act of observation appears to change reality. Physicists have debated what this means for decades. Eugene Wigner, a physicist, wanted to explore this idea further. He imagined a situation where one observer measures a quantum system, while another observer watches the first observer. This creates a problem. If quantum mechanics is correct, then before the first observer looks at the system, it exists in a superposition. But what happens when the first observer makes a measurement? According to standard quantum theory, the system collapses into one state. The observer sees a clear result. However, from Wigner's perspective, the first observer and the quantum system together are still in a superposition. This means that, for Wigner, the measurement has not yet happened in a definite way. The first observer may think the measurement is complete, but Wigner sees them as part of a larger quantum system. Both perspectives seem valid, yet they conflict with each other. A simple example can make this clearer. Imagine a lab with a physicist inside. The physicist is Wigner's friend. In the lab, the physicist conducts an experiment on a quantum particle. The particle can be in two possible states, and until measured, it exists in both at the same time. The physicist records the result and sees a definite answer. Outside the lab, Wigner doesn't know what happened inside. From his point of view, the entire lab, including his friend and the experiment, must still be in a superposition. In Wigner's reality, no single measurement has taken place yet. But inside the lab, Wigner's friend has already seen a result. They both experience different versions of reality. This paradox creates a fundamental problem. In classical physics, if two people observe the same event, they should agree on what happened. Reality should not depend on who is looking. But Wigner's friend paradox suggests that reality itself might be subjective. If quantum mechanics applies to large systems, then different observers can see different outcomes, and both can be correct. This idea has been tested in experiments. In 2019, a group of physicists performed a version of Wigner's thought experiment. They created pairs of entangled photons, which are particles of light linked together in a quantum state. Different observers measured these photons in separate locations. The results showed that two different observers could record conflicting outcomes. The measurements confirmed that, at least in a controlled quantum system, reality could indeed be relative. This challenges the idea of an objective, fixed world. It suggests that what we call reality depends on how and when we observe it. Some interpretations of quantum mechanics embrace this idea. The many worlds interpretation, for example, proposes that every time a measurement happens, reality splits. One observer sees one outcome, and another observer sees a different one in a separate branch of reality. Both versions exist, but they do not interact. Other interpretations try to avoid this conclusion. Some physicists argue that consciousness plays a role in collapsing quantum states. They suggest that once a conscious being observes a system, superposition disappears and reality becomes definite. This idea is controversial and lacks experimental proof. There are also philosophical implications. If Wigner's paradox is correct, then different people might truly experience different realities in ways we do not yet understand. This could mean that what we call objective facts are only true within specific reference frames. In daily life, we assume that facts exist independently of who observes them. But in the quantum world, facts may not be absolute. This paradox also raises questions about communication between observers. If Wigner and his friend compare notes, what happens? In theory, when Wigner checks the lab, the superposition collapses, and he sees a single outcome. But until that moment, both versions exist. Some physicists argue that when information is shared, reality becomes consistent for all observers. Others suggest that inconsistencies remain, challenging our understanding of knowledge itself. The paradox also connects to larger mysteries in physics. Quantum mechanics and relativity are the two most successful theories in modern science, but they do not fully agree with each other. General relativity describes a universe where time and space are continuous and objective. Quantum mechanics suggests a world where probabilities rule and reality depends on measurement. Wigner's paradox highlights this gap. It hints that our current theories might be incomplete. This experiment also raises practical concerns for quantum computing. Quantum computers rely on superposition to perform calculations. If different observers can experience different results, then how does one ensure that a quantum computation gives a definite answer? Scientists designing quantum systems must consider these fundamental questions. The paradox suggests that our understanding of measurement needs revision. In classical physics, measurement is straightforward. A ruler measures length, a clock measures time, and everyone agrees on the results. In quantum mechanics, measurement appears to change reality. Wigner's paradox takes this to an extreme, suggesting that even the act of recording a result might not settle the question of what truly happened. There are many open questions. Some researchers believe that future experiments will clarify whether this paradox reflects a real feature of nature or a flaw in our understanding. Others think that a new theory, possibly a deeper version of quantum mechanics or a theory of quantum gravity, will resolve these contradictions. For now, Wigner's friend paradox remains one of the most puzzling thought experiments in modern physics. It challenges our deepest assumptions about reality, observation, and knowledge. It suggests that reality might not be as fixed as we once thought. A quantum system can exist in multiple states at the same time. This is called superposition. But when we measure the system, we see only one definite outcome. This is the measurement problem. It raises a big question. When and why does a quantum system move from being in many states to just one? Imagine a simple experiment. A single electron moves through space. It behaves like a wave, spreading out and existing in multiple places at once. If we do not measure it, it stays in this uncertain state. But the moment we measure where it is, we find it in just one place. The wave-like behavior disappears. It is as if the act of measurement forces the electron to choose a definite position. This idea challenges how we think about reality. In everyday life, things have definite positions. A ball on a table does not exist in many places at once. But at the quantum level, particles do not have fixed locations until measured. Before measurement, they exist as probabilities. A famous example of this is the double-slit experiment. If we send electrons toward a barrier with two slits, they pass through like waves and create an interference pattern on a screen behind them. The pattern shows that each electron behaves as if it goes through both slits at once. But when we place a detector at the slits to see which one each electron passes through, the pattern disappears. Instead, electrons behave like particles, going through one slit or the other, but never both. The act of measuring changes how they behave. Physicists describe this change as wave function collapse. The wave function is a mathematical equation that describes all possible states of a quantum system. Before measurement, it includes all possibilities. After measurement, it collapses to a single definite state. But what causes this collapse? That is the core of the measurement problem. One interpretation is that observation itself forces collapse. This idea, linked to the Copenhagen interpretation, suggests that quantum systems stay in superposition until observed. Some physicists take this literally and argue that a conscious observer is necessary. But this leads to strange questions. Does an unmeasured particle have no real properties? And what counts as an observer? A camera? A human? A single photon bouncing off an atom? Others argue that interaction with the environment forces collapse. This idea is called decoherence. A quantum system is delicate. When it interacts with the world, such as air molecules or light, it loses its quantum nature and takes on definite properties. Decoherence explains why large objects do not show quantum weirdness. A table consists of countless particles, all interacting and collapsing each other's wave functions. That is why we never see a table in a superposition of two locations. Another explanation is the many worlds interpretation. Instead of collapse, it proposes that all possible outcomes happen, but in different branches of reality. If we measure an electron's position, we see one outcome, but another version of us sees a different outcome in another universe. This idea removes the need for collapse, but leads to a different puzzle. Where do these other worlds exist, and how could we ever test this idea? A famous thought experiment highlights the measurement problem. Schrödinger's cat describes a cat inside a box with a quantum-triggered poison device. The quantum system is in superposition, meaning the poison is both released and not released. If quantum rules apply, the cat should be both alive and dead until we open the box. But this seems absurd. The cat is big, made of many atoms, and should not exist in such an uncertain state. Yet, if the cat follows quantum mechanics, it should be in superposition. This raises the question: when does quantum uncertainty end and classical reality begin? Experiments have tested wave function collapse using larger and larger objects. Scientists have put tiny molecules into quantum superposition, showing interference patterns like electrons. As experiments push toward larger scales, the boundary between quantum and classical behavior remains unclear. Another issue is whether collapse is a real physical event or just a change in our knowledge. Some theories propose that collapse is a physical process, like a particle snapping into place. Others suggest it is only our perception that changes, while reality remains uncertain at deeper levels. Some physicists propose new physics to explain collapse. Objective collapse models suggest that wave functions collapse randomly over time, independent of observers. These models predict slight deviations from standard quantum mechanics, which experiments might one day detect. The measurement problem remains unresolved. Different interpretations offer different solutions, but no single explanation has been proven. Quantum mechanics works in practice, but why it works this way remains a mystery. Scientists continue to explore this question, looking for clues in experiments and new theories. The No-Cloning Theorem states that it is impossible to create an exact copy of an unknown quantum state. This rule comes from the fundamental principles of quantum mechanics. It may seem strange because in the world we experience, copying information is easy. A document can be printed, a digital file can be duplicated, and even biological cells can be cloned. But in the quantum world, things work differently. To understand why perfect copying is impossible, it helps to first think about what a quantum state is. A quantum state describes a particle in terms of probabilities. Unlike classical objects, which have definite properties, a quantum system exists in a superposition of possibilities. When someone measures the system, the superposition collapses and the system takes on a definite state. But before measurement, all possibilities exist together. Consider a simple example: a photon. A particle of light can have two polarization states, horizontal or vertical, but it can also be in a superposition, meaning it is partly horizontal and partly vertical at the same time. The exact nature of this superposition is delicate. If someone tries to measure the photon's polarization, the superposition collapses into a definite state. If someone tries to copy the photon without disturbing it, they run into a fundamental problem. Imagine a machine that tries to copy an unknown quantum state. If the state is already known, copying is simple. But if the state is unknown, things become tricky. The copier does not know whether the photon is horizontal, vertical, or in a superposition. Because measurement collapses a quantum state, any attempt to gather full information about it destroys the original superposition. This is why quantum copying is fundamentally different from copying classical objects. To see why perfect cloning is impossible, consider what would happen if it were allowed. Suppose there was a machine that could make exact quantum copies. A scientist could use this machine to copy a quantum system many times and perform measurements on the copies. By comparing the results, they could determine the original state without ever disturbing it. This would violate a core principle of quantum mechanics, which states that an unknown quantum state cannot be fully determined without being altered. Another way to see the problem is through mathematics. In classical physics, copying information is straightforward. A document contains words, and making a copy simply transfers those words to another piece of paper. In quantum mechanics, however, the state of a system is described by a mathematical object called a wave function. The No-Cloning Theorem shows that no physical process can take an arbitrary wave function and create an identical, independent copy of it. The process of duplication would require knowledge of the wave function, but measuring it collapses the state. The contradiction means perfect copying is impossible. This has profound consequences. One major impact is in quantum computing. A quantum computer processes information using qubits, which exist in superpositions. If a qubit could be copied, quantum information could be duplicated like classical data. But because the no-cloning theorem prevents perfect copying, quantum computers must operate differently. Instead of traditional error correction techniques, they rely on quantum error correction codes that work without making perfect copies. The no-cloning theorem also plays a key role in quantum cryptography. In classical encryption, an eavesdropper can copy a message without the sender or receiver knowing. But in quantum encryption, the inability to clone quantum states ensures security. If an eavesdropper tries to copy a quantum key, they inevitably disturb it, revealing their presence. This principle is the basis for quantum key distribution, where two parties share a secure cryptographic key without fear of undetected interception. A useful way to think about the no-cloning theorem is through an analogy. Imagine a delicate ice sculpture that represents a quantum state. The sculpture is so fragile that any attempt to touch or examine it alters its shape. If someone wants to make a perfect replica, they cannot simply press a mold against it, because the mold would deform the original. Without full knowledge of the exact shape beforehand, creating an exact copy is impossible. Quantum teleportation offers an interesting comparison. Although perfect cloning is forbidden, quantum information can still be transferred from one place to another using a process called quantum teleportation. This method involves entanglement, a phenomenon where two particles share a connection no matter how far apart they are. In quantum teleportation, information about a quantum state is transmitted to another location, but the original state is destroyed in the process. This respects the no-cloning theorem because it moves quantum information rather than duplicating it. Experiments have confirmed the no-cloning theorem many times. Scientists working with photons, atoms, and superconducting circuits have repeatedly found that attempts to perfectly copy quantum states always fail. Instead, partial copies can sometimes be made, but these are imperfect and contain only limited information about the original. Despite its restrictions, the no-cloning theorem does not prevent all forms of copying. Certain types of quantum information can be transferred using approximate cloning, where a less-than-perfect copy is made. These imperfect copies can be useful in specific applications, but never fully recreate the original quantum state. The implications of the no-cloning theorem extend beyond technology. It shapes our understanding of quantum mechanics itself. It tells us that quantum information behaves differently from classical information, and that certain intuitive ideas, like perfect replication, do not apply in the quantum world. This difference is why quantum mechanics leads to results that seem counterintuitive compared to everyday experience. The no-cloning theorem is one of the many ways quantum mechanics challenges expectations. It highlights the fundamental limits of knowledge and the ways in which quantum systems resist classical interpretation. Whether in computing, cryptography, or the nature of reality itself, the impossibility of cloning quantum states remains a defining principle of modern physics. The proton is one of the fundamental building blocks of matter. It is found in the nucleus of every atom and, along with neutrons and electrons, makes up everything we see around us. In classical physics, protons are considered stable, meaning they never decay into other particles. However, some grand unified theories in particle physics suggest that protons should decay over long periods. If protons decay, this would mean that even the most stable matter in the universe will eventually disappear. The problem is that no one has ever observed a proton decay. This raises a paradox. If our theories predict that protons are unstable, but experiments show they remain intact, does this mean our understanding of physics is incomplete? The idea of proton decay comes from attempts to unify the fundamental forces of nature. Scientists know of 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. In the early universe, these forces may have been unified, acting as a single force. As the universe cooled, they split into separate forces, each governing different aspects of nature. Grand unified theories, or GUTs, try to bring the strong, weak, and electromagnetic forces together under a single framework. These theories suggest that at extremely high energies, such as those found in the early universe, protons might not be as stable as once thought. According to some versions of GUTs, protons should decay over incredibly long timescales. A proton might transform into lighter particles, such as positrons and pions, through a process that is extremely rare. If true, this means that every proton in the universe has a tiny chance of decaying at any given moment. While the lifetime of an individual proton might be billions or even trillions of times the age of the universe, with enough protons in existence, some should have decayed by now. But so far, no experiment has detected a single instance of proton decay. To test for proton decay, scientists build massive detectors. These experiments require large amounts of matter because the process is so rare. A famous example is the Super Kamiokande experiment in Japan, a giant underground tank filled with 50,000 tons of ultra-pure water. If a proton decays inside this water, it should produce detectable flashes of light. The experiment has been running for decades, but no proton decay has been observed. This suggests that if proton decay happens, it is even rarer than some theories predicted. The lack of observed proton decay has consequences. Many grand unified theories predicted proton lifetimes on the order of 10 Kuturigwen to 10 Tufurigwer years. Since experiments have failed to see any decay, physicists have placed new lower limits on proton lifetimes, extending them to at least 10 per 4 years. This means some proposed theories are likely incorrect. If protons decay at all, it happens far less frequently than expected. This raises the question of whether protons are truly stable or if they decay at rates too low for current technology to detect. If protons eventually decay, it would mean that all atoms in the universe are doomed to fall apart. Even the most stable elements, like iron, would eventually break down into lighter particles. Over unimaginable timescales, the universe would lose all its matter, leaving behind only radiation. This idea leads to speculation about the far future of the cosmos. If matter itself is unstable, the ultimate fate of the universe may be very different from what we currently assume. The idea of proton decay is closely tied to the search for a deeper understanding of physics beyond the Standard Model. The Standard Model is the most successful theory of particle physics, describing all known particles and their interactions. However, it does not include gravity and does not naturally explain why protons appear to be stable. Many physicists believe that the Standard Model is incomplete and that a more fundamental theory is needed to explain all the forces of nature. If proton decay is eventually observed, it would provide strong evidence for physics beyond the Standard Model. One reason why proton decay is expected in GUTs is that the strong nuclear force, which holds atomic nuclei together, may not be as permanent as once thought. In these theories, particles called X-bosons mediate interactions that allow protons to transform into other particles. These X-bosons are predicted to be incredibly massive, which is why proton decay is so rare. Since no experiment has seen an X-boson, some scientists question whether they exist at all. There are alternative explanations for why protons appear stable. Some theories suggest that an unknown symmetry of nature prevents protons from decaying. In physics, symmetries often explain why certain particles behave the way they do. For example, the conservation of electric charge ensures that charged particles like electrons do not suddenly disappear. If protons are protected by a similar conservation law, this could explain their observed stability. If this is the case, then proton decay may never be found because it does not happen. Another possibility is that proton decay exists, but at an even slower rate than predicted. If the true lifetime of a proton is 10^4 or 10^6 years, it would take even larger experiments to detect it. Future detectors, like the proposed Hyper-Kamiokande, could extend our search by increasing the amount of matter under observation. These experiments might eventually detect a rare proton decay event, confirming the predictions of grand unified theories. If proton decay is real, it could also have implications for the early universe. In the moments after the Big Bang, conditions were far more extreme than today. If protons were unstable in those conditions, they might have played a role in shaping the evolution of the cosmos. The process of proton decay could be connected to why the universe contains more matter than antimatter, an unsolved mystery in physics. If protons decayed slightly differently than their antiparticles, it could explain why matter dominates the universe instead of being annihilated by antimatter. The search for proton decay is also linked to the broader effort to discover new physics. Experiments that test proton stability also search for other rare processes, like neutrino interactions and dark matter particles. By studying these rare events, scientists hope to uncover new physics that could lead to a more complete understanding of the universe. The paradox remains unresolved. Our best theories suggest protons should decay, but experiments show they do not, at least not at the predicted rate. This gap between theory and observation is a sign that our understanding of fundamental physics is incomplete. Whether future experiments will detect proton decay or force physicists to rethink their theories remains an open question. The answer could reshape our view of the universe and its ultimate fate. Entropy is the measure of disorder in a system. The second law of thermodynamics states that entropy always increases over time in an isolated system. This means the universe should be moving toward a state of higher disorder. Yet, complex and ordered structures exist everywhere. Stars form, galaxies take shape, and life emerges on Earth. This seems to contradict the law of increasing entropy. If everything moves toward disorder, how does complexity arise? To understand this, imagine a room filled with gas molecules. Over time, the molecules spread out evenly, creating a uniform distribution. This is an example of increasing entropy. The system moves from an ordered state, where molecules might be clustered in one area, to a disordered state, where they are randomly spread. This is what the second law describes. Left alone, systems tend toward disorder. But life does not seem to follow this pattern. A living cell is highly organized. It has complex structures, such as DNA, proteins, and organelles, all working together in precise ways. If the universe moves toward disorder, how does something as structured as a cell form? The same question applies to galaxies, planets, and weather systems. These structures do not seem random. They follow specific patterns and show a kind of order that should not exist if entropy always increases. The key to resolving this paradox is understanding how entropy applies to open systems. The second law applies to isolated systems, which means no energy or matter enters or leaves. The universe as a whole is an isolated system, but most things within it are not. Earth, for example, receives energy from the sun. This constant flow of energy allows complex structures to form and persist. While local order increases, the overall entropy of the universe still rises. Take a tree as an example. A seed grows into a towering oak over decades. It absorbs sunlight, takes in nutrients from the soil, and pulls carbon dioxide from the air. All these processes build complexity, but at the same time, the tree releases heat and waste into the environment. The total entropy of the universe increases, even though the tree itself becomes more organized. The local decrease in entropy does not violate the second law because it is balanced by a greater increase in entropy elsewhere. Another way to think about this is with a refrigerator. The inside of the fridge stays cold and organized, while the back of the fridge releases heat into the surrounding air. The appliance increases order inside by using energy, but it also increases the total entropy of the room. The cooling process does not violate the second law because the overall disorder in the system, including the fridge and its surroundings, still increases. Life operates in a similar way. Organisms use energy from the sun or from food to maintain order. Cells repair themselves, replicate DNA, and build complex molecules. These processes decrease entropy locally, but they require energy input. That energy comes from the breakdown of food or sunlight, both of which increase entropy elsewhere. The total entropy of the universe continues to rise, even though life appears to resist disorder. This pattern extends beyond biology. Stars form when gravity pulls gas and dust together. This seems like a decrease in entropy because the particles become more concentrated. But as a star forms, it releases massive amounts of heat and radiation, increasing entropy in its surroundings. The same principle applies to galaxies, hurricanes, and even cities. These systems appear to defy entropy, but they actually contribute to its increase on a larger scale. Think about cooking an egg. The egg starts in an ordered state, with the yolk and white separated. When you apply heat, the proteins unfold and form a new structure. The cooked egg is more complex, but the heat from the stove increases entropy in the kitchen. The total disorder of the system, including the air, the pan, and the food, has increased. This paradox also connects to the idea of evolution. Over millions of years, life has developed from simple molecules to complex organisms. If entropy increases, why does evolution move toward complexity instead of randomness? The answer lies in natural selection. Evolution is not a random process. It builds on previous structures, refining and improving them over time. The energy input from the environment allows life to maintain complexity while still following the rules of thermodynamics. Consider a river carving a canyon. At first, the land is relatively smooth. Over time, the flowing water erodes the rock, creating intricate patterns and deep channels. The process follows physical laws, but it results in structures that look complex. In the same way, life's complexity emerges from simple rules applied over long timescales. Entropy does not mean everything must break down immediately. It means that, over time, systems tend to move toward higher disorder unless energy is added. A sandcastle on the beach erodes because the wind and waves push it toward a more probable, disordered state. But with effort, a person can rebuild the castle. This requires energy and work, just as life requires energy to maintain its order. Another useful analogy is a deck of cards. If you shuffle a new deck, the order becomes more random. This follows the principle of entropy. But what if you sort the cards back into order? That requires effort. You are using energy to counteract the natural trend toward disorder. Similarly, living systems use energy to maintain structure. Entropy also plays a role in the aging process. A young organism is highly ordered, with functional cells and efficient systems. Over time, errors accumulate in DNA, proteins degrade, and the body's repair mechanisms become less effective. This gradual breakdown follows the rules of entropy. Living things must constantly work to maintain order, but eventually, entropy takes over. Even though entropy increases, localized complexity can still emerge. The key is energy flow. Whether in biology, physics, or chemistry, complex structures appear when energy moves through a system. The sun fuels life on Earth. Gravity drives star formation. Natural selection refines life forms. Each of these processes increases entropy overall, even as they create pockets of order. The entropy reversal paradox is not really a contradiction. It only seems paradoxical when looking at small parts of the system in isolation. When viewed as a whole, entropy always increases, even as local complexity arises. The universe follows consistent laws, allowing order to emerge naturally within a broader trend of increasing disorder. Curry's paradox is a logical problem that arises from self-referential statements. It shows how a simple sentence can lead to contradictions. The paradox exists in natural language and formal logic, creating problems in systems that try to avoid inconsistencies. To understand Curry's paradox, start with a basic self-referential statement. Imagine someone saying, "If this sentence is true, then the moon is made of cheese." This sentence creates an unusual situation. If the sentence is true, then its conclusion must also be true. If it is false, there is no contradiction, but the sentence itself does not provide a clear way to determine its truth. This paradox works because it follows valid rules of logic, yet leads to an absurd result. The problem appears in formal logic when statements refer to themselves in a way that forces a conclusion. Consider a sentence written in logical form. If this statement is true, then 2 plus 2 equals 5. If we assume the statement is true, then according to logic, 2 plus 2 must equal 5, which is false. However, if we assume the statement is false, then it doesn't tell us anything, and we can't determine its truth value. This self-referential nature is what makes Curry's paradox unique. It differs from other logical paradoxes, like the liar paradox, which states, "This sentence is false." The liar paradox creates a direct contradiction, because if the sentence is true, then it must be false, and if it is false, then it must be true. Curry's paradox does not create a contradiction. Instead, it manipulates logical rules to make any conclusion appear true. To see why this is a problem, apply it to a real-world scenario. Imagine a legal system where a law states, if this law is valid, then all crimes are forgiven. If the law is valid, then every crime must be forgiven, which seems unreasonable. If the law is not valid, then it does not apply, but nothing about the structure of the statement itself prevents the absurd result from occurring. Mathematicians and logicians have long struggled with self-referential statements. Russell's paradox, which involves sets that contain themselves, led to major revisions in set theory. Curry's paradox presents a different challenge because it does not rely on negation or contradiction. Instead, it follows a pattern of reasoning that looks valid but leads to an unreasonable conclusion. One way to see how Curry's paradox works is by breaking it into steps. Suppose we have a sentence P that says, if P is true, then unicorns exist. To analyze this logically, assume P is true. If P is true, then the statement inside the conditional must also be true, meaning that unicorns must exist. But the truth of P depends only on its structure, not on any evidence of unicorns. This allows the paradox to prove things that are not logically connected. Formal logic tries to prevent these problems by using restrictions on self-reference. Some systems limit how statements can refer to themselves to avoid unintended conclusions. However, Curry's paradox shows that even in carefully structured logical systems, strange results can emerge. In mathematics, some versions of logic exclude certain forms of self-referential statements to prevent such paradoxes. The paradox also raises questions about truth and implication. Normally, if a statement says, if A, then B, we assume that A and B have some logical connection. Curry's paradox allows any statement to be inserted into the conclusion, making it appear true without evidence. This challenges the idea that implication should always follow logical reasoning. Computers and programming languages also face problems related to self-referential logic. If a program includes a function that calls itself under certain conditions, it may never stop running. This is similar to how Curry's paradox forces a system into an endless loop of logical consequences. Some philosophers and logicians argue that Curry's paradox reveals weaknesses in how we define truth. If truth can be manipulated in this way, does it mean that some statements are neither true nor false? Or does it mean that implication needs to be redefined to avoid absurd conclusions? These questions remain open in certain areas of logic. Mathematics has methods to avoid paradoxes like Curry's. Some logical systems include rules that prevent statements from referring to themselves in certain ways. Others redefine how implication works, requiring that a conditional statement only holds if the two parts are logically connected. These solutions work in specific contexts, but the paradox remains an important example of how logic can lead to surprising results. Another way to approach the problem is through language. Everyday speech contains many self-referential statements that do not cause paradoxes. If someone says, "I always tell the truth," we do not assume that their statement can prove unrelated facts. But in formal logic, self-referential statements can create contradictions when handled without restrictions. Curry's paradox has implications for philosophy as well. If logic can produce contradictions, does that mean logic itself is flawed? Some philosophers argue that paradoxes like this suggest that human reasoning has limits. Others see paradoxes as opportunities to refine and improve logical systems. The paradox is named after Haskell Curry, a logician who studied self-referential statements. His work contributed to important discussions in logic, and his name is also associated with Curry's combinatory logic, a mathematical system that simplifies functions. Although Curry did not invent the paradox, his studies brought attention to it, leading to further research. Understanding Curry's paradox helps reveal the complexity of logic and reasoning. It shows that even simple statements can lead to surprising consequences when carefully analyzed. The paradox also serves as a reminder that logical reasoning, while powerful, must be used carefully to avoid unintended results. The Allais Paradox shows how people make choices that don't follow expected utility theory. This theory says that when faced with uncertainty, people should make decisions that maximize their expected gains. But in real-world situations, people often behave differently. Their choices change based on how options are presented, even when the actual outcomes are the same. This suggests that people don't always act in a purely rational way when dealing with probability and risk. To understand the paradox, consider a simple lottery choice. Suppose you have two options. In the first option, you can receive $1 million for sure. In the second option, you have a 10% chance of getting nothing, an 89% chance of getting $1 million, and a 1% chance of getting $5 million. Many people choose the first option because they prefer a guaranteed reward over a gamble, even if the gamble offers a small chance of a much larger prize. Now consider a different choice. In this case, you can choose between a 10% chance of winning nothing and a 90% chance of winning $1 million. The other option is a 10% chance of winning nothing, an 89% chance of winning $5 million, and a 1% chance of winning $1 million. Here, many people switch their choice and prefer the second option. This happens even though the change in probability between these two cases is the same. This shift in decision-making contradicts expected utility theory, which predicts that people should evaluate these choices consistently. This paradox shows that people value certainty much more than probability suggests they should. The certainty of getting $1 million in the first case feels more valuable than the higher expected payoff of the gamble. But when certainty is removed, people become more willing to take risks. This behavior does not align with expected utility calculations, which suggests that rational individuals should always maximize their mathematical expectation. The Allais paradox challenges the idea that people always make rational choices when dealing with uncertainty. It suggests that psychological factors influence decision-making in ways that traditional economic models do not account for. For example, the fear of losing out on a guaranteed reward can outweigh the potential benefits of a high-risk, high-reward situation. This explains why many people prefer secure investments over riskier but potentially more profitable opportunities. One way to see this effect in everyday life is in insurance decisions. Many people buy insurance for low-cost items, even though in the long run they would save more money by not purchasing coverage. The psychological comfort of knowing they won't have to pay for a replacement outweighs the mathematical expectation of saving money. This mirrors the way people respond to the certainty of receiving $1 million versus taking a small risk for a much greater reward. This paradox also appears in gambling and investing. Many people avoid high-risk, high-reward investments, even when they have a strong chance of being profitable. Instead, they prefer stable, low-return investments because they feel safer. However, when the situation changes and all options involve some level of risk, people become more open to higher risks. This shift in behavior reveals the inconsistency in decision-making that the Allais paradox describes. Another example involves medical decisions. Suppose a patient has two treatment options. The first treatment guarantees survival with a slightly lower quality of life. The second treatment has a 90% chance of leading to a better outcome, but a 10% chance of death. Many people choose the guaranteed outcome, even though the second option offers a higher expected benefit. If the same patient were given a different set of choices, where both options involve some risk, they might make a different decision, even though the mathematical probabilities remain unchanged. The paradox also challenges traditional economic theories that assume people always act in their best financial interest. In reality, people's choices are influenced by their emotions, the way options are framed, and their aversion to loss. This helps explain why some people make financial decisions that don't maximize their expected wealth. They may prioritize avoiding regret, ensuring security, or reducing anxiety over making the most profitable choice. In behavioral economics, the Allais Paradox has led to new theories about decision-making under uncertainty. One such theory is prospect theory, which suggests that people evaluate gains and losses differently. People tend to fear losses more than they value equivalent gains. This is known as loss aversion. It explains why people avoid risks that might lead to even a small loss, even if the overall expected value is positive. One real-world application of the Allais paradox can be seen in lottery participation. Many people buy lottery tickets even though the expected value of a ticket is negative. The reason is that the small chance of winning a huge jackpot feels disproportionately valuable. In contrast, those same people might refuse to invest in the stock market, even when historical data shows it has a much higher expected return. The paradox also affects public policy. Governments and businesses use this knowledge when designing policies and marketing strategies. For example, insurance companies highlight the certainty of coverage to appeal to people's preference for security. Similarly, policymakers frame messages about health and safety in ways that emphasize guarantees rather than probabilities. In risk management, understanding the Allais paradox helps businesses make better decisions. Companies must account for how employees, customers, and stakeholders perceive risk, not just how they should logically evaluate it. A company that assumes people will always choose the mathematically optimal choice may make poor strategic decisions. By recognizing that people's risk preferences change depending on how choices are framed, businesses can design better policies and communication strategies. Another example is seen in legal settlements. A person facing a lawsuit may be offered a guaranteed settlement or a chance to go to court for a larger payout. Many people take the settlement because they prefer certainty, even if the expected value of going to trial is higher. However, if both options involve some level of risk, such as different levels of settlement offers, people's choices may shift in unexpected ways. The Allais paradox also applies to negotiations. A negotiator may prefer a guaranteed deal even if a better offer could be possible with some risk. Understanding this tendency can help negotiators frame offers in ways that appeal to the other party's risk preferences. In engineering and safety planning, this paradox helps explain why people sometimes overreact to small risks while ignoring larger but less immediate dangers. For example, people may worry more about rare but dramatic accidents than about common risks like heart disease or car crashes. This influences public safety campaigns and regulatory policies, which must account for how people perceive risk rather than just the actual statistical probabilities. Understanding the Allais paradox reveals how human decision-making often departs from strict mathematical reasoning. People's choices depend on how options are framed, their fear of losing a guaranteed reward, and their changing risk preferences. This paradox has broad implications in fields ranging from economics and psychology to public policy and business strategy. It highlights the importance of studying real-world behavior rather than relying solely on theoretical models of rational choice. Bertrand's paradox is a problem in probability theory that shows how different methods for picking a random chord in a circle can lead to different results. It challenges the idea of randomness and shows that probability depends on how you define a selection process. The paradox was introduced by Joseph Bertrand in 1889 and remains an important example of ambiguity in probability. To understand this paradox, imagine a circle drawn on a piece of paper. You want to randomly select a chord, which is a line connecting 2 points on the circle. Then, you want to determine the probability that the length of this chord is longer than the side of an inscribed equilateral triangle. The side of this triangle is equal to the radius of the circle multiplied by the square root of 3. The question seems straightforward, but the result depends entirely on how you define random. One method to choose a random chord is to pick 2 points on the circumference at random and draw a line between them. If you use this method, the probability of getting a chord longer than the side of the equilateral triangle is 1/3. A second method is to choose a random point inside the circle and then draw a chord that is perpendicular to the radius at that point. If you follow this approach, the probability changes to 1/2. A third method is to select a random midpoint for the chord in circle. The chord is then drawn so that it passes through this midpoint. Using this definition of randomness, the probability becomes 1/4. These three methods lead to different probabilities for the same question, which seems to violate the idea that probability should be well defined. The key issue here is that the concept of a random chord is not as simple as it seems. The problem does not specify a single way to generate a chord, so different interpretations produce different answers. To see why the probabilities differ, consider how each method distributes the chords differently. In the first method, where you pick two random points on the circle's edge, all possible chords have equal likelihood based on uniform placement of their endpoints. However, this method tends to favor shorter chords because points near each other produce shorter segments. The second method, where a random point is chosen and the chord is drawn perpendicular to a radius, spreads chords more evenly across different lengths. Chords that are longer than the triangle's side appear more frequently than in the first method. This shifts the probability toward a higher value. The third method, where the midpoint of the chord is randomly selected, emphasizes shorter chords. Since a longer chord requires the midpoint to be closer to the center of the circle, there are fewer ways to generate long chords compared to short ones. This leads to a lower probability of getting a chord that exceeds the triangle's side. This paradox highlights an important concept in probability. The way you define randomness affects the outcome. It also shows that probability problems are not always as objective as they seem. If a problem does not clearly define the process of random selection, different interpretations can produce different answers. Consider an everyday example of a similar issue. Suppose you are asked to select a random person in a city. How do you do it? One way is to pick a random name from a phone book. Another way is to stand on a busy street and select the next person who walks by. A third way is to randomly choose a house and then interview the first person inside. Each of these methods may seem reasonable, but they will produce different results because they do not sample people in the same way. The same principle applies to Bertrand's paradox. Without a clear definition of randomness, there is no single correct probability. This issue appears in other areas of probability and statistics, especially in fields like physics and economics, where assumptions about random processes can change the interpretation of data. Mathematicians have debated whether one method of choosing a random chord is more correct than the others. Some argue that the second method, where the chord is drawn perpendicular to a radius at a random point, is the most natural because it preserves symmetry in the distribution of chords. Others believe that all three methods are valid and that the paradox simply exposes an ambiguity in the question rather than a contradiction in probability theory. Bertrand's paradox also has implications for real-world applications of probability. In physics, probability distributions often depend on the way a system is modeled. In statistics, the way data is collected influences conclusions. For example, in surveys, how questions are asked and how samples are selected can change the results significantly. This paradox also plays a role in computer science, particularly in algorithms that generate random samples. If a computer program needs to generate a random chord in a circle for a simulation, the programmer must specify the method of selection. Different choices will lead to different statistical outcomes. Bertrand's paradox challenges intuition because it reveals that probability is not always an absolute concept. Instead, probability depends on how randomness is defined. The paradox forces people to think critically about what it means for something to be random, and highlights the importance of precise definitions in probability problems. The St. Petersburg Paradox describes a situation where a simple lottery game has an infinite expected value, yet people are unwilling to pay much to play. It challenges the way people think about probability, value, and decision-making. Imagine a game where a fair coin is flipped repeatedly until it lands on heads. The number of times the coin lands on tails before heads determines the payout. The rules are simple. If the first flip is heads, the player wins $2. If it takes 2 flips to get heads, the player wins $4. If it takes 3 flips, they win $8. The winnings keep doubling for every extra tails before heads appears. The game continues indefinitely until heads appears. The expected value of the game comes from probability and payout calculations. The probability of getting heads on the first flip is half. The probability of getting tails first and then heads is quarter. The probability of getting 2 tails before heads is wets. The payout follows a pattern. 1 flip gives $2, 2 flips give $4, 3 flips give $8, and so on. The expected value is the sum of all possible payouts multiplied by their probabilities. Each term simplifies to 1. Since there are infinite terms, the sum grows without limit. This means the expected value of the game is infinite. A rational person should, in theory, be willing to pay any price to play, since the potential winnings outweigh any finite cost. But in practice, most people would not pay much. Many would hesitate to pay even $10. Casinos would not offer the game if players were willing to pay large amounts because they would expect to lose money. The paradox appears because mathematical expectation suggests an infinite value, while real-world decision-making suggests otherwise. One reason people hesitate is that large payouts are unlikely. A $1,000 payout requires a streak of 10 tails before heads. The probability of that happening is 1 in 1,024. A $1 million payout requires a streak of 20 tails. The chance of that happening is about 1 in a million. While the expected value is infinite, the chance of making a large profit is low. Most players will win small amounts before the game ends. Another reason is that people do not think in purely mathematical terms when making decisions. Expected value calculations assume that every dollar is worth the same, no matter how much a person has. In reality, money has diminishing utility. A person values the first few dollars they receive much more than later dollars. Winning $100 is exciting for most people, but winning $1,010 instead of $1,000 does not feel much different. This effect means that even though the game has infinite expected value, it does not feel worth an infinite amount. A thought experiment helps illustrate this. Imagine a billionaire and a person with only $50. The billionaire might be willing to pay $1,000 to play because they can afford to lose it. The person with $50 would hesitate to pay even $10, since losing that money affects them more. This shows that different people value money differently, and expected value does not capture personal circumstances. The paradox also raises questions about rational decision-making. If the expected value is infinite, why do most people refuse to play for high stakes? Some argue that people are not purely rational when dealing with probability. Instead of looking at expected value, they focus on likely outcomes. The most common result of the game is winning a small amount, so people do not see it as worth a high price. Others argue that real-world constraints make the paradox unrealistic. A casino or banker offering the game would run into practical limits. No one has infinite money to pay out large winnings. If a player needed to collect $1 billion, the casino might not have the funds. If payouts are capped at a certain amount, the expected value is no longer infinite, which removes the paradox. A related idea comes from decision theory. The paradox suggests that people use a different model for decision-making called expected utility rather than expected value. Expected utility accounts for how much a person values money rather than treating every dollar equally. If winning $1,000 does not feel 10 times as valuable as winning $100, then the decision to play depends on more than just expected value. This idea helps explain why people are cautious with risky bets, even when the math suggests they should take them. History provides examples of similar paradoxes in gambling and finance. Lotteries and casinos offer games with negative expected value, yet people still play because they focus on the small chance of a large reward. Stock markets show another example. Some investments have positive expected value, but high risk, making people hesitant to invest even when the math suggests they should. These real-world behaviors align with how people react to the St. Petersburg game. Alternative versions of the game highlight the paradox in different ways. If the payouts grow more slowly, the expected value becomes finite, and people's choices align better with the math. If payouts grow faster, the paradox becomes even more extreme. Some experiments have tested how people react to similar games, showing that most people do not consider expected value alone when making decisions. This paradox also connects to modern economic and psychological research. Behavioral economics explores why people make decisions that seem irrational from a mathematical perspective. Studies show that people overweight small probabilities and underweight large ones. For example, people fear plane crashes even though they are rare, but ignore more common risks like car accidents. This tendency explains why the small chance of a large payout in the St. Petersburg game does not make people willing to pay large amounts. Risk aversion plays a role as well. Most people prefer a guaranteed small reward over a risky large one. If given a choice between receiving $50 for sure or playing a game with a 50% chance of winning $100, many would take the guaranteed money. Even though both choices have the same expected value, certainty feels safer. Philosophers and mathematicians have debated the paradox for centuries. Daniel Bernoulli, who first described the problem, suggested that expected utility, not expected value, explains the issue. He proposed that the usefulness of money decreases as a person gains more of it. This idea led to modern utility theory, which influences fields like economics and finance. Some researchers have tried modifying the game to make it more realistic. One version adds a maximum payout limit, which removes the infinite expectation. Another limits the number of coin flips, making it easier to predict likely outcomes. These versions align better with how people think about risk and reward in real life. The paradox remains a useful tool for exploring probability and decision-making. It shows that expected value alone does not always determine choices. It highlights the role of utility, risk, and psychology in decision-making. While the math suggests that playing the game is always worthwhile, human behavior tells a different story. The three prisoners paradox is a problem in probability that leads to surprising results. It involves three prisoners, each hoping for a pardon. The paradox arises when one of them tries to improve his chances by using conditional probability, only to find that the outcome is not what he expected. Imagine three prisoners, A, B, and C, on death row. They know that the governor will pardon one of them, chosen at random, while the other two will be executed. The warden knows who will be pardoned but cannot reveal it directly. Prisoner A wants to improve his odds, so he comes up with a strategy. He reasons that since one of the three will be freed, his chance of being pardoned is 1 in 3. He then asks the warden to name one of the other two prisoners, B or C, who will definitely be executed. The warden, knowing the outcome, names C. Now, prisoner A believes that the situation has changed. He reasons that before the warden revealed this information, his chance of being pardoned was 1 in 3. But now, he sees that the pardon must go to either himself or prisoner B. Since one of the two will certainly be freed, he assumes the probability has shifted and that he now has a 50% chance instead of 33%. This reasoning seems logical, but it is incorrect. The actual probability that prisoner A will be pardoned remains 1 in 3, while prisoner B's chance has increased to 2 in 3. This counterintuitive outcome is what makes the three prisoners paradox so puzzling. To understand why this happens, consider the information that the warden provides. The warden must always name someone who will be executed. He cannot name the person who will be pardoned. That means if prisoner A was originally doomed, the warden would have only one choice. He must name the other prisoner who will be executed. If prisoner B was the one to be pardoned, then the warden had two choices. He could name either A or C. But no matter what, prisoner A's odds of being pardoned do not change from the original 1 in 3. A different way to think about it is to compare this problem to a similar one called the Monty Hall problem, a well-known probability puzzle from game shows. In Monty Hall, a contestant chooses one of 3 doors, behind one of which is a prize. The host, who knows where the prize is, then opens one of the remaining 2 doors that does not have the prize. The contestant is then given the choice to stick with their original door or switch. Many people assume the odds are now 50-50, just like prisoner A does, but the reality is different. The probability of winning by switching is actually 2 in 3. This happens because the host's action is not random, it is based on prior knowledge. The warden in the Three Prisoners Paradox behaves in a similar way. His action does not give prisoner A new information about his own chances of being pardoned, but does provide insight into prisoner B's likelihood. Another way to explain this is by considering all possible scenarios. Before the warden reveals anything, the odds of being pardoned are equally split. 1/3 for prisoner A, 1/3 for prisoner B, and 1/3 for prisoner C. The warden's action does not change the fact that one of these three must be pardoned. Instead, it eliminates one of the doomed prisoners from consideration, which affects the remaining odds. Suppose the pardon was always predetermined and the warden knew the outcome. If prisoner A was chosen for the pardon, the warden could name either B or C as a doomed prisoner. If prisoner B was chosen for the pardon, the warden would always have to name C. If prisoner C was chosen for the pardon, the warden would always have to name B. Since prisoner A's fate never influences how the warden chooses whom to name, prisoner A's chances remain the same. However, prisoner B benefits because there was a case where the warden could have named either B or C. The fact that he chose C means prisoner B's probability shifts in his favor. The paradox highlights how conditional probability can challenge intuition. Many people assume that removing an option means the odds must adjust evenly between the remaining choices, but probability does not always work that way. When the warden names a doomed prisoner, he is not picking at random. He is following a rule based on information that is not visible to prisoner A. That unseen information influences the probability in a way that is easy to overlook. People often struggle with conditional probability because they rely on instincts rather than formal calculations. It seems natural to assume that eliminating an option automatically distributes its probability among the remaining choices. However, when the elimination process is not random but based on hidden knowledge, the situation changes. This paradox serves as a reminder that probability can behave in ways that defy simple expectations. To make this even clearer, consider another analogy. Imagine three friends enter a raffle with 3 tickets. Each person takes 1 ticket at random. Before revealing the winner, an official who knows the outcome discards 1 losing ticket and announces who owned it. If one of the remaining 2 ticket holders assumes that their probability of winning has now increased to 50%, they would be mistaken. The chance that the remaining ticket belongs to the winner is not evenly split. It depends on how the official selected the ticket to remove. The Three Prisoners Paradox teaches a valuable lesson about how probability works when new information is introduced. It demonstrates that eliminating an option does not always mean the remaining choices become equally likely. The way that information is revealed can shape probability in ways that are not immediately obvious. This problem continues to challenge people because it contradicts common sense, but its logic holds when examined carefully. Parrondo's paradox describes a situation where 2 losing strategies, when combined, can create a winning strategy. This idea seems impossible at first because losing should always lead to more losing. However, under certain conditions, alternating between bad choices can produce long-term gains. The paradox appears in game theory, physics, and even real-world systems like finance and biology. To understand the paradox, imagine 2 games. Each game has rules that lead to a net loss over time. If you play either game on its own for a long period, you will lose money. But if you switch between the 2 games in a particular sequence, you start to win. This contradicts intuition because losing strategies should not lead to a winning outcome. The paradox highlights how randomness and probability can combine in surprising ways. Consider a simple coin flipping game. Suppose game A uses a biased coin that lands on heads 49% of the time and tails 51% of the time. If you bet on heads, you will lose more often than you win, leading to an overall loss. Game B is more complicated. It uses 2 coins, one that is heavily biased against you and another that slightly favors you. The game switches between these 2 coins depending on how much money you have. If your balance is a multiple of 3, the game uses a very unfavorable coin that lands on heads only 10% of the time. If your balance is not a multiple of 3, the game uses a coin that lands on heads 75% of the time. On its own, this game also leads to losses because you frequently get stuck using the bad coin. If you play game A repeatedly, you lose. If you play game B repeatedly, you also lose. But if you alternate between the two games in the right pattern, something surprising happens. Instead of losing money, you start to win over time. The interaction between the two games creates fluctuations in your balance that prevent you from getting stuck in the worst parts of game B. This shifting allows you to take advantage of the moments when you have a higher chance of winning, leading to overall gains. This paradox applies to many real-world situations. In finance, investors sometimes use strategies that involve alternating between risky and conservative investments. If they stay too long in one type of investment, they might see consistent losses. But if they move between different asset classes at the right times, they can generate long-term gains even when individual investments perform poorly. In biology, natural selection sometimes works in a similar way. Some species thrive by switching between different survival strategies. For example, a predator might alternate between hunting different types of prey. If it only hunts one species, it may deplete its food source and starve. But by switching prey periodically, it avoids exhausting any single resource and ensures long-term survival. This kind of adaptive behavior mirrors the mechanics of Parrondo's paradox. The paradox also appears in physics. Certain systems, like Brownian ratchets, use similar principles to create directed motion from random fluctuations. A Brownian ratchet is a theoretical device that allows random molecular motion to produce useful work. Normally, random motion should not lead to net movement in one direction, but under specific conditions, alternating forces can create steady progress. This effect is similar to how switching between losing games can produce winning results. Understanding why Parrondo's paradox works requires thinking in terms of probability and long-term patterns rather than individual events. In the coin flipping example, each game has different probabilities that influence the player's balance in different ways. Game A consistently moves the player toward losses. Game B also tends to cause losses, but does so in a way that depends on the player's current state. When the two games interact, the losses from one game can help avoid the worst outcomes of the other, allowing the player to escape negative cycles. This principle applies beyond simple games. Many complex systems benefit from variation and periodic change. In economics, businesses that adapt their strategies based on market conditions tend to perform better than those that follow a single rigid plan. A company that only invests in safe assets may miss opportunities for high returns, while a company that only takes risks may go bankrupt. By balancing between the two approaches, businesses can achieve better outcomes over time. Even human behavior follows similar patterns. People who focus too much on either short-term gains or long-term stability often struggle to maintain success. Those who constantly chase high-risk opportunities may experience early gains, but eventually fail due to unsustainable decisions. On the other hand, those who avoid all risk may never experience significant growth. Alternating between calculated risk-taking and stability can lead to better results, much like the alternating strategy in Parrondo's paradox. Another example involves physical exercise. A person who follows only one type of workout may not see optimal results. For instance, someone who only lifts heavy weights might build strength but lack endurance. Someone who only does cardio might have good endurance but weak muscles. However, by alternating between strength training and cardio, they can achieve balanced fitness gains. This mirrors the paradox, where switching strategies leads to better long-term performance. Parrondo's paradox also challenges how people think about probability and decision-making. Many assume that a losing strategy must always result in losses, but this paradox shows that context and timing play a crucial role. The way different elements interact can produce outcomes that seem impossible when looking at each part in isolation. This concept has led researchers to explore applications in various fields. In neuroscience, some studies suggest that the brain may use similar alternating strategies to optimize learning and problem solving. In genetics, certain mutations that are harmful in one environment may become beneficial when conditions change. In social dynamics, alternating between cooperation and competition can lead to more stable and productive relationships. The paradox highlights an important lesson. individual choices do not always determine the final outcome on their own. The way different choices interact over time matters just as much. Systems that seem doomed to fail can sometimes succeed when their elements are combined in the right way. By understanding these principles, people can make better decisions in areas ranging from finance to fitness to strategic planning. The Borel-Kolmogorov Paradox comes from probability theory and highlights a strange issue with conditional probability. It shows how the way we condition on events can lead to different answers, depending on how we approach the problem. This paradox is subtle, but it reveals a deep issue in probability and measure theory. To understand the paradox, consider a simple case of probability. Suppose you have a fair six-sided die. If you roll it, each number from 1 to 6 has an equal chance of appearing. Now, imagine you know that the number rolled is even. That means the possible outcomes are 2, 4, or 6. Since each of these three numbers was equally likely before you learned this information, the probability of any one of them occurring is now 1/3. This example is straightforward because we are conditioning on a discrete event. But probability also applies to continuous situations, like picking a random point on a circle. Here, conditional probability behaves differently and can give conflicting results. Imagine a sphere, like a globe. A random point is chosen on this sphere, meaning every location is equally likely. Now you receive new information. The point lies on the equator. The question is, what does this tell you about where the point is along the equator? Intuitively, you might think that if the original choice was truly random, then once you learn the point is on the equator, every location along the equator should be equally likely. That means a uniform distribution, where the probability of the point appearing in any segment of the equator depends only on the length of the segment. This seems reasonable because nothing in the original setup favored one part of the equator over another. However, probability theory does not always work the way intuition suggests. The paradox arises when you apply the formal rules of conditional probability. One way to define probability mathematically is through conditional density functions. But if you try to use this approach here, you find that different methods lead to different results. In other words, depending on how you define the conditional probability, you might get a uniform distribution along the equator, or you might get a different distribution altogether. This happens because the probability measure on the sphere does not behave the same way as probability in a finite setting, like rolling dice. In continuous spaces, probability is tied to measure theory, and conditioning on events that have zero probability in the original space, like the equator in this case, requires special handling. The paradox highlights that without carefully defining what it means to condition on such an event, you can arrive at inconsistent answers. To see this issue more clearly, imagine another version of the problem. Instead of choosing a random point on a sphere, suppose you pick a random latitude first. Once you have a latitude, you then pick a random point on that latitude circle. Now you condition on the fact that the latitude happens to be 0, which means the point lies on the equator. If you started with a uniform choice over all latitudes, the probability distribution along the equator would no longer be uniform. Instead, it would follow a different rule based on the original process that selected the latitude. In contrast, if the point were chosen directly on the sphere, then restricting to the equator would lead to a uniform distribution. These two methods are mathematically different, but both are reasonable ways to model the problem. This subtle distinction is what creates the paradox. The method you use to define conditional probability affects the final result, even when dealing with the same underlying event. This goes against everyday intuition, where we expect probability to work the same way no matter how we describe a situation. One way to resolve the paradox is to recognize that probability in continuous spaces does not behave the same way as in discrete cases. In the die example, the probability of rolling an even number was originally 3/6 or 1/2, and conditioning on an even number simply redistributed that probability among three outcomes. In continuous spaces, however, probabilities are represented by density functions, not simple fractions, and conditioning on a zero probability event requires extra care. Another important lesson from the paradox is that probability distributions do not just depend on outcomes, but also on how those outcomes are generated. In the equator example, the probability of picking a specific longitude depends on whether the original process selected a latitude first or not. This dependence is not obvious at first, but it shows why different methods of conditioning can lead to different answers. The paradox is not just a curiosity. It has implications for statistics, physics, and even philosophy. In Bayesian probability, which deals with updating beliefs based on new information, the choice of how to condition on events matters. If two different approaches lead to different answers, it raises the question of which approach is correct. In physics, probability plays a role in quantum mechanics and statistical mechanics, where conditioning on certain measurements can change outcomes in unexpected ways. In real-world applications, these differences can affect how models are built. Consider meteorology, where weather models predict future conditions based on current data. If a model conditions on certain observations in a way that does not properly account for measure-theoretic effects, it might give misleading forecasts. In machine learning, where probability plays a role in algorithms that make predictions, different ways of defining conditional probabilities can influence outcomes. The Borel-Kolmogorov Paradox reminds us that probability is not just about numbers. It is about how we define and interpret events. In simple cases like rolling a die, probability behaves predictably. But in more complex scenarios, especially involving continuous spaces, the way we frame a problem affects the answer. This paradox highlights a deep and often overlooked aspect of probability theory, showing that even fundamental concepts can lead to surprising and conflicting results. Newcomb's paradox is a thought experiment in decision theory. It presents a scenario where free will and game theory seem to contradict each other. A player must make a choice, but the presence of a near-perfect predictor makes the decision unclear. The paradox has been widely debated in philosophy, economics, and mathematics. The setup is simple. A player is presented with two boxes. Box A is transparent and contains $1,000. Box B is opaque, and it either contains $1,000 or nothing. The player can choose to take only box B or take both boxes. The twist is that a highly intelligent predictor has already made a decision about the contents of box B. If the predictor expected the player to take both boxes, box B is empty. If the predictor expected the player to take only box B, it contains $1,000. The predictor has an extremely high accuracy rate, nearly 100%. It has successfully predicted choices in the past. The player knows this. Now they must decide which option to take. On one hand, it seems logical to take both boxes. After all, box A always contains $1,000, and the contents of box B have already been determined. Choosing both boxes guarantees at least $1,000, and if box B has the million, then the total becomes $1,001. But on the other hand, if the predictor is accurate, taking both boxes means box B is empty. This means the player only gets $1,000 instead of $1,000. Many people argue that the best strategy is to take only box B. Since the predictor is nearly perfect, choosing only box B means it almost certainly contains $1,000. Those who favor this reasoning believe that the player's choice is not really free. Instead, it is part of a pattern that the predictor has already analyzed. By choosing only box B, the player follows the logic that leads to the largest payout. Others argue that the correct choice is to take both boxes. They claim that since the contents of box B are already determined, the best move is to maximize gains by taking both. This reasoning follows the idea of dominance in game theory. No matter what box B contains, taking both boxes always results in at least $1,000 more than taking only one. This paradox puts free will to the test. If the player believes in free will, then they should assume that their choice is independent of the predictor's past decision. That would mean that box B already contains what it does, and taking both boxes is the best move. But if the predictor is nearly perfect, then the player's decision is effectively predetermined. In that case, taking only box B ensures the highest reward. An example can make this clearer. Imagine that a scientist has studied a person's behavior for years. Every time they play a game, the scientist predicts what they will do with near-perfect accuracy. The person now faces Newcomb's problem. If they take both boxes, the scientist will have already predicted that and placed nothing in box B. If they take only box B, the scientist will have foreseen that too and placed $1,000 inside. Now, imagine this game has been played many times before. The predictor has made hundreds of predictions with a perfect record. Every time a player takes only box B, they receive $1,000. Every time a player takes both boxes, they end up with only $1,000. Seeing this pattern, what should the next player do? If they rely on past evidence, they should take only box B. But if they think of the game as a one-time decision where past outcomes do not matter, they might take both. The paradox raises questions about determinism. If the predictor is truly perfect, then the player does not actually have a choice. Their decision is part of a predetermined sequence. But if free will exists, then the predictor should not be able to know with certainty what the player will do. The paradox forces people to question whether their choices are truly independent, or if they are part of a larger system that has already accounted for their decisions. Another way to look at the problem is through expected outcomes. If a player assumes the predictor is always right, then taking only box B should result in $1,000. If they assume the predictor is unreliable, then taking both boxes should result in at least $1,000. This leads to a divide between two reasoning styles. Some people trust the statistical pattern and choose only box B, while others rely on logical dominance and choose both. Newcomb's paradox is similar to other decision problems. It relates to the prisoner's dilemma, where two rational players make choices that lead to worse outcomes because they act in their own self-interest. It also connects to issues in artificial intelligence and predictive modeling. If a machine could perfectly predict human choices, what would that mean for free will? Would humans still have autonomy, or would their decisions simply follow a pre-programmed path? This paradox has real-world implications. In markets, people make decisions based on predictions of future events. If a trader believes that their actions are independent, they may make moves based on immediate gains. But if they believe that the market follows predictable trends, they may change their approach. The same logic applies to behavior in elections, negotiations, and even personal decisions. Some philosophers argue that the paradox exposes a flaw in the way people think about time. The contents of box B have already been determined before the player makes their choice. This suggests that their decision does not actually influence the outcome. But if the predictor is accurate, then the choice seems to retroactively determine what was placed in box B. This backward-in-time reasoning conflicts with standard logic, but is common in discussions about free will and determinism. A practical way to test the paradox is through simulations. If a computer model predicts choices with high accuracy, then players who take only box B should end up with more money on average. If the predictor's accuracy drops below a certain threshold, then taking both boxes might become the better strategy. This suggests that the paradox depends on how much trust one places in the predictor's ability. Newcomb's paradox remains unsolved because it challenges fundamental ideas about choice, prediction, and causality. Some favor the one-box strategy because historical evidence suggests it leads to higher rewards. Others favor the two-box strategy because they believe in maximizing gains based on existing conditions. The paradox does not have a definitive answer, which is why it continues to be a subject of debate. The lottery paradox highlights a conflict between reasonable beliefs. It starts with something simple. In a fair lottery with thousands or even millions of tickets, each ticket has an extremely low chance of winning. It seems rational to believe that any single ticket will lose. If a person looks at ticket number 1, they can reasonably say it will lose. The same goes for ticket number 2, ticket number 3, and so on. If they go through the entire set of tickets, each one appears to be a loser. But at the same time, they also know that one ticket must win. This creates a contradiction. If someone believes every ticket will lose, they should also believe that no ticket will win. But that's false, because the rules of the lottery guarantee a winner. To see this more clearly, imagine a lottery with 100,000 tickets. a person holds one ticket and examines their chances. The odds of winning are 1 in 100,000, which is tiny. They consider this and say, this ticket will almost certainly lose. They are not wrong. If they repeat the reasoning for every ticket, they come to the same conclusion for each one. But at the end, they have declared that all 100,000 tickets are losers. That contradicts the fact that one of them must win. This problem shows up in real-world reasoning all the time. People make decisions based on probabilities and sometimes apply their reasoning inconsistently. A similar situation appears in legal cases. A jury may look at evidence and determine that the probability of someone committing a crime is low. Maybe they are 99% sure the person is guilty, but the legal system requires proof beyond a reasonable doubt. The question then arises, if every case has some small uncertainty, can a jury ever be absolutely certain of guilt? If they doubt every case, then no one should ever be convicted. But that contradicts the idea that guilty people should be punished. The same pattern appears in other areas where people must balance low probabilities against certainty. Another example comes from medical diagnoses. A doctor sees a patient with symptoms matching a rare disease. The odds of having this disease are low. Maybe only 1 in a million people get it. The doctor reasons that this patient likely does not have the disease, just as they would reason for every other patient. But some people do get the disease. If every doctor dismissed every case as unlikely, no one would ever get diagnosed. Again, a contradiction emerges between rational individual beliefs and what must happen in reality. The lottery paradox also raises questions about how people define rationality. If a belief is rational, it should be consistent with other rational beliefs. But in this case, a person can hold two reasonable beliefs that contradict each other. They can rationally believe that every ticket will lose, and also rationally believe that one ticket must win. Some philosophers argue that this shows a flaw in the way humans think about probabilities. Others suggest that rational belief should not be treated as an all-or-nothing concept. Instead, belief should be based on degrees of certainty. Instead of saying, this ticket will lose, a person could say, this ticket is extremely unlikely to win. This shift avoids the paradox because it allows for some uncertainty. One way to explore this paradox further is to think about a larger lottery. Imagine a country holds a national lottery with 1 billion tickets. The odds of winning are now even smaller. If a person buys one ticket, their chance of winning is 1 in a billion, which is practically 0. It seems even more reasonable to believe that their ticket will lose. But even in this case, one ticket must win. The same contradiction appears no matter how large the lottery becomes. People often rely on shortcuts when thinking about probability, and this paradox reveals a common mistake. When they say, this ticket will lose, they are treating a high probability as a certainty. But probability does not work that way. Even if something is extremely unlikely, it is not impossible. This confusion affects decision-making in everyday life. A person might avoid a certain activity because the odds of success are low, even though low odds do not mean 0 chance. This kind of thinking appears in investing, job applications, and personal choices. Someone might avoid applying for a job because they think they have little chance of being hired, even though someone must get the job. They assume their failure before even trying, based on reasoning similar to the lottery paradox. The paradox also relates to how people handle risk. In insurance, companies calculate probabilities for different events. They assume that most people will not crash their cars, have their houses burned down, or face major medical emergencies. If they followed the lottery paradox logic, they might decide that no one needs insurance because each person's risk is low. But in reality, some people will experience these events, and insurance exists to cover those cases. The same applies to public health measures. A government might look at a rare disease and decide that most people will not get it. If they conclude that no one will get it, they might fail to prepare, which could lead to disaster if the disease spreads. The paradox also plays a role in scientific research. When scientists conduct experiments, they use statistics to determine how likely a result is to be real rather than random chance. If the odds of a result happening by chance are very low, they assume it is significant. But every experiment has some probability of error. If researchers followed the reasoning of the lottery paradox, they might doubt every result. This could lead them to reject findings that are actually true, just because there is a small chance they are mistakes. Understanding the lottery paradox helps people recognize limitations in their reasoning. It shows why treating probabilities as certainties leads to contradictions. It also highlights why decisions should be based on degrees of belief rather than absolute statements. The paradox does not just apply to lotteries. It appears in law, medicine, finance, and everyday decision-making. By recognizing this pattern, people can think more clearly about probabilities and avoid drawing incorrect conclusions. Simpson's paradox describes a situation where a trend appears in separate groups of data, but disappears or reverses when the groups are combined. This happens because percentages and averages can be misleading when they don't account for how data is divided. It can affect statistics in medicine, social sciences, and even sports. The paradox challenges assumptions about data and how people interpret numbers. Imagine two hospitals treating a particular disease. Hospital A has a higher survival rate than Hospital B for both mild and severe cases. If a patient has a mild case, they are more likely to survive at Hospital A. If they have a severe case, they are still more likely to survive at Hospital A. But when looking at the overall survival rate, Hospital B has a better record. This result seems impossible at first, but the key is how many patients each hospital treats in each category. Suppose Hospital A specializes in severe cases and treats far more critical patients. These patients have a lower survival rate overall, even if Hospital A does a better job treating them than Hospital B. Hospital B, on the other hand, treats mostly mild cases, which have a naturally high survival rate. When all cases are combined, Hospital B appears to perform better, even though it has worse survival rates in every category. The numbers tell different stories depending on whether they are grouped or separated. The same paradox appears in college admissions. A university has two departments, science and arts. More male students apply to science, and more female students apply to arts. Science has a lower acceptance rate overall, while arts has a higher one. If more men apply to the department with the lower rate and more women apply to the department with the higher rate, it might look like the university is rejecting more women overall. But when looking at each department separately, the acceptance rate for men and women might be almost identical. Sports statistics also show Simpson's paradox. A baseball player might have a higher batting average than another player in two separate seasons, but a lower overall batting average when the seasons are combined. This can happen if the player with the higher averages had fewer at-bats in one season, while the other player had more chances during a season where their performance was better. To see how this works with actual numbers, imagine two baseball players, Allais and Bob. In the first half of the season, Allais gets 30 hits out of 100 at-bats, while Bob gets 25 hits out of 100. Allais's batting average is 0.30, and Bob's is 0.25. In the second half of the season, Allais gets 1 hit out of 10 at-bats, while Bob gets 50 hits out of 200 at-bats. Allais's batting average for the second half is 0.10, while Bob's is 0.25. In both halves, Allais has a better average, but when the total is calculated, Allais has 31 hits in 110 at-bats, giving her an overall average of 0.281. Bob has 75 hits in 300 at-bats, giving him an average of 0.25. Now Bob appears to be the better hitter. This happens because the second half of the season had far more at-bats. Bob had a steady performance across both halves, while Allais's average was heavily affected by a small number of attempts. The paradox shows why it is important to consider how data is weighted. Simpson's paradox also appears in economics and salary comparisons. Suppose two companies, one small and one large, employ men and women in two different departments, management and general staff. In both departments, women have higher average salaries than men. But when combining the salaries from both departments, men appear to earn more. This can happen if more men work in management, where salaries are higher, while more women work in general staff positions. The numbers suggest a pay gap that does not exist when broken down into groups. This problem also affects medical studies. A drug might appear to work better for all patient groups when analyzed separately, but seem less effective when the groups are combined. If the treatment group contains more high-risk patients and the control group contains more low-risk patients, the overall data might suggest the drug is less effective, even if it actually works better for every individual category. Election results can also be misleading because of this paradox. Suppose a candidate wins in every district when votes are counted separately, but loses when all votes are combined. This can happen if voter turnout varies across districts. If the candidate wins in districts with fewer voters and loses in districts with more voters, the overall numbers may show a loss despite victories in individual areas. The paradox highlights how data can be misinterpreted. It warns against drawing conclusions from raw percentages without considering how groups are structured. It is not enough to compare overall averages or totals. It is important to look at how data is divided and how different sample sizes affect results. The same numbers can tell different stories depending on how they are grouped. When analyzing statistics, understanding the context behind the numbers is crucial. Without context, data can be misleading, and decisions based on misleading data can be flawed. The replication crisis is a serious issue in modern science. It refers to the fact that many scientific studies, especially in psychology, medicine, and social sciences, fail to produce the same results when tested again. This raises concerns about how reliable scientific findings are. The problem affects the foundation of research because replication is one of the key principles of the scientific method. If results cannot be repeated, then the original findings might not be as solid as they first appeared. The issue became widely known in the early 2010s when researchers started re-examining well-known experiments. In psychology, the Open Science Collaboration attempted to replicate 100 key studies and found that more than half of them did not hold up. This shocked many scientists. If a study claims that a particular treatment reduces anxiety or that a certain factor affects decision-making, other researchers should be able to repeat the experiment and get the same result. But often they don't. This raises an important question. Why do so many studies fail to replicate? There are several possible explanations. One major factor is statistical power. Many studies use small sample sizes, which means they might detect an effect by chance, rather than because something real is happening. Imagine flipping a coin only 5 times and getting 4 heads. That might lead to the conclusion that heads is more likely than tails, but with more flips, the pattern would disappear. The same problem happens in research. Small studies might show strong effects that are actually just random variation. Another issue is p-hacking. Scientists often use a statistical threshold called p.05 to determine if a result is significant. If the p-value is below 0.05, the result is considered meaningful. But this system creates pressure to find results that fit this standard. Some researchers unintentionally manipulate data or adjust their analyses until they reach significance. This can include practices like selectively reporting only the data that supports a hypothesis or running multiple tests and only publishing the ones that produce a positive result. These practices don't necessarily mean a scientist is being dishonest, but they introduce bias into research. Publication bias also plays a role. Journals tend to prefer studies that show strong, surprising, or positive results. If a researcher tests a hypothesis and finds no effect, that study is less likely to be published. As a result, the scientific literature may be filled with studies that show effects that seem much stronger than they really are. This gives the impression that a certain drug works better than it does, or that a psychological phenomenon is more powerful than it actually is. Consider a study that claims eating a particular type of berry improves memory. If 10 researchers conduct this experiment, and one finds a significant effect while the other 9 find no effect, the one positive study is more likely to be published. The public might see headlines about the superfruit that boosts your brain, without realizing that most studies found no benefit at all. When another group tries to replicate the result, they might not find the same effect because it was never there to begin with. Even high-profile studies have been affected by the replication crisis. One famous example is the work on power posing, which suggested that standing in a confident posture for a few minutes could change hormone levels and improve decision-making. The original study gained widespread attention, including a TED Talk that received millions of views, but later research failed to confirm these findings. Many scientists now believe the original study may have overstated its claims. The replication crisis is not limited to psychology. In medicine, many clinical trials fail to produce the same results when repeated. A study on cancer research found that only a small percentage of key findings could be successfully replicated. This is particularly concerning because medical decisions often rely on these studies. If a drug is approved based on research that later turns out to be unreliable, it could have serious consequences for patients. In economics, well-known studies have also faced replication failures. For example, one influential paper claimed that countries with high debt levels experience slower economic growth. Policymakers used this finding to justify austerity measures. But when other researchers re-examined the data, they found major flaws in the calculations. The result was not as clear-cut as originally claimed. Social sciences face similar problems. Many famous studies on human behavior and decision-making have struggled to replicate. This includes research on how subtle cues influence people's actions, such as the idea that seeing a picture of eyes makes people behave more honestly. Some follow-up studies have not been able to reproduce these effects, leading scientists to question how strong they really are. One of the main challenges in addressing the replication crisis is the way science is structured. Researchers are often rewarded for publishing new and exciting findings rather than for confirming old ones. Replication studies are less likely to be published, even though they are essential for verifying results. This creates a system where scientists have little incentive to double-check past research. Some fields are taking steps to improve the situation. In psychology, researchers are now pre-registering their studies. This means they publicly state their research plan before they collect data, making it harder to change methods after seeing the results. More journals are also encouraging replication studies, recognizing that science needs both new discoveries and confirmation of past findings. Technology is also playing a role in fixing the problem. Open science initiatives encourage researchers to share their data and methods so others can verify their work. Some studies now use larger sample sizes to ensure more reliable results. There is also a growing push to change the way statistical significance is used, with some scientists arguing that rigid thresholds like p0.05 should be replaced with more flexible approaches. Despite these efforts, the replication crisis remains a serious challenge. It forces scientists to ask difficult questions about which findings can be trusted and how research should be conducted. The issue does not mean that science is broken, but it does highlight the need for better practices. When studies fail to replicate, it does not necessarily mean the original findings were fraudulent or useless. In many cases, it simply shows that science is a process of refinement. Early results are often uncertain, and it takes multiple studies to build a clear understanding. The replication crisis reminds scientists and the public that one study is rarely enough to prove something. Reliable knowledge comes from patterns of evidence, not single experiments. This means that people should be cautious when reading about groundbreaking discoveries, especially in areas like health, psychology, and economics. If a new study claims to have found an amazing effect, it is important to ask whether other researchers have found the same thing. Science is meant to be self-correcting, and replication is a key part of that process. The challenge is ensuring that researchers, journals, and institutions prioritize replication just as much as they prioritize new discoveries. By recognizing the importance of replication, researchers can build a more reliable foundation for scientific knowledge. The universe appears to be fine-tuned for life. The fundamental constants of physics, such as the strength of gravity, the charge of the electron, and the nuclear forces inside atoms, fall within a very narrow range that allows complex structures like galaxies, planets, and living organisms to exist. If any of these values were even slightly different, stars would not form, planets would not develop stable orbits, and life as we know it would be impossible. This raises an unsettling question. Why does the universe have these specific conditions when the odds of such precise values occurring randomly seem impossibly low? One possible answer is that life exists simply because the conditions allow it to. If the universe were different, intelligent beings would not be around to observe it. This is known as the anthropic principle. It states that the physical laws of the universe must be compatible with the existence of observers, because otherwise there would be no one to notice them. The paradox emerges because this explanation seems unsatisfying. It does not reveal why the universe has these conditions. It only explains why we should not be surprised to see them. Imagine throwing a dart at a wall covered in billions of tiny squares. If only one square allows life to exist and you hit that square perfectly, you might wonder how such an unlikely event occurred. The anthropic principle suggests that the question is meaningless because, had you missed, you wouldn't be here to ask it. But this response does not resolve the deeper mystery of why that one square existed in the first place. Some scientists suggest that there may be an enormous number of universes, each with different physical laws. This idea, known as the multiverse theory, proposes that our universe is just one of countless others. Most universes would be lifeless because their physical constants would not support complex structures. But if enough universes exist, at least some of them will have conditions that allow life to emerge. The fact that we live in one of those universes would then be inevitable rather than surprising. A common analogy is a lottery. If millions of people buy tickets, someone is almost guaranteed to win, even though the chances for any individual person are tiny. If our universe is just one among many, then it is not surprising that at least one exists where life is possible. We just happen to live in that particular universe. However, there is no direct evidence that other universes exist. The multiverse remains a theoretical idea, not a proven fact. Some critics argue that proposing an infinite number of universes does not explain why the physical constants take their observed values. It only shifts the question elsewhere. If different universes have different laws, what mechanism determines those laws? Why do they vary in the way they do? Another possibility is that the apparent fine-tuning of the universe is an illusion. Perhaps the laws of physics could not have been different. Some theories in fundamental physics suggest that the values of physical constants are determined by deeper mathematical principles. If this is true, then asking why the universe has these specific conditions would be like asking why a triangle has 3 sides. The question would have no real meaning because the answer would be built into the nature of reality. There is also the idea that life could adapt to different conditions. Perhaps we assume that life must look like it does on Earth, requiring carbon-based molecules, liquid water, and a stable climate. But what if life could form under very different conditions, using silicon instead of carbon, or thriving in extreme environments that seem uninhabitable to us? In that case, the universe might not be as finely tuned for life as it appears. It may simply be suited to the kind of life we recognize. Looking at Earth itself offers another perspective. The conditions that allowed humans to evolve are incredibly specific. Our planet orbits a stable star at just the right distance to support liquid water. The atmosphere has the right mix of gases for breathing. The planet has a magnetic field that protects it from harmful radiation. A giant planet like Jupiter exists in the outer solar system, deflecting dangerous asteroids. If any of these factors were different, life on Earth might never have arisen. Yet, Earth is just one planet among billions in our galaxy, and our galaxy is one among billions in the universe. Even if the chances of a habitable planet forming are low, the vast number of planets increases the odds that at least one will have the right conditions. From this perspective, the fine-tuning of Earth may not be surprising at all. It might simply be a case of probability playing out on a massive scale. The problem with fine-tuning arguments is that they assume the universe had to be designed in a specific way for life to exist. But what if the conditions we see are just one possible outcome among many? If the laws of physics were different, a different kind of universe might exist with its own unique phenomena. Maybe intelligent beings in that universe would wonder why their own conditions seemed so special. There is also the possibility that we do not yet fully understand the origins of the universe. The laws of physics as we know them emerged after the Big Bang. But what determined those laws? Were they set randomly, or did some deeper principle fix them in place? If our understanding of physics is incomplete, then the question of fine-tuning may be premature. Future discoveries could reveal that the universe's properties are not as improbable as they seem. One of the most intriguing aspects of this paradox is its connection to consciousness. The universe is filled with stars, galaxies, and empty space, yet it also contains thinking beings capable of asking questions about existence. If life were just a random byproduct of natural processes, would it be so common? Or does the presence of intelligence suggest something deeper about the structure of reality? Some interpretations of quantum mechanics suggest that observers play a fundamental role in shaping reality. The famous double-slit experiment shows that particles behave differently depending on whether they are observed. This raises the strange possibility that consciousness might influence the physical world at a fundamental level. If this is true, then perhaps the universe is fine-tuned for life, because life is somehow necessary for the existence of the universe itself. Even if this idea is speculative, it highlights how little we understand about the nature of reality. The Anthropic Paradox forces us to question our assumptions about existence, probability, and the role of intelligence in the cosmos. It challenges us to think about whether life is an accident of physics or an essential feature of the universe. For now, the question remains open. Scientists continue to search for answers, whether through exploring fundamental physics, searching for extraterrestrial life, or probing the limits of human knowledge. The fine-tuning of the universe remains one of the most puzzling mysteries in modern science. Whether it points to a deeper principle, a multiverse, or an unknown process that set the conditions for life, it continues to inspire debate and discovery. The question of how the first self-replicating molecule emerged is one of the most fundamental mysteries in biology. Life depends on molecules that can copy themselves, but before life existed, there was no system to guide replication. This creates a paradox. How did the first molecule capable of replication arise naturally when replication itself seems necessary for evolution to shape complex molecules in the first place? The most widely accepted idea is that the first self-replicating molecule was RNA. This is known as the RNA world hypothesis. Unlike DNA, RNA can both store genetic information and act as a catalyst for chemical reactions. In modern cells, RNA plays an essential role in reading and translating genetic instructions. Some types of RNA, called ribozymes, can even copy short strands of RNA without the help of proteins. This suggests that early life may have relied on RNA before proteins and DNA evolved. The problem is that RNA is a complex molecule. It consists of a long chain of nucleotides, each made of a sugar, a phosphate group, and a nitrogenous base. Forming these components under prebiotic conditions is difficult. Some experiments have shown that nucleotides can form under simulated early Earth conditions, but assembling them into long RNA strands without the help of enzymes is another challenge. In a modern cell, specialized enzymes build RNA and DNA, but in a prebiotic world, those enzymes did not exist. Some researchers propose that simpler molecules may have preceded RNA. These molecules, sometimes called proto-RNA, might have been able to copy themselves in a less efficient way. Over time, they could have evolved into RNA-like molecules that were better at replication. The challenge is identifying which molecules could have played this role and demonstrating how they could have formed naturally. Another possibility is that self-replication did not start with a single molecule, but with a network of molecules working together. In this view, a set of simple molecules could have catalyzed each other's formation in a kind of cooperative cycle. Over time, these interactions may have led to the emergence of more complex molecules capable of storing information and copying themselves. A key part of the paradox is that life needs both information and function. DNA stores genetic instructions, but it needs proteins to copy itself. Proteins perform almost all the work in a cell, but they need DNA to be built. RNA offers a solution because it can both store information and catalyze reactions. But the question remains, how did RNA or a similar molecule emerge without an existing system to support it? Some scientists think that mineral surfaces may have played a role. Certain types of clay can attract and organize organic molecules. Experiments have shown that nucleotides can link together on clay surfaces, forming short strands of RNA-like material. If this happened on early Earth, it could have helped build the first self-replicating molecules. However, linking nucleotides is not enough. The molecule must also be able to copy itself accurately, or errors will accumulate and prevent long-term stability. Another challenge is energy. Replication requires energy input, and early Earth lacked the complex biochemical machinery that modern cells use to fuel their processes. Some researchers suggest that naturally occurring chemical gradients, such as those near hydrothermal vents, could have provided the necessary energy. These environments are rich in minerals and chemical reactions that produce energy, making them a possible birthplace for self-replicating molecules. The issue of replication accuracy also presents a problem. If an early molecule could copy itself but made too many mistakes, useful information would be lost. Modern cells have error-correcting mechanisms that reduce mutations, but the first self-replicating molecules had no such system. For life to begin, there had to be a balance between mutation and stability. Too many errors would prevent useful sequences from surviving, but some variation was necessary for evolution to occur. There is also the question of stability. RNA is fragile compared to DNA. In water, it breaks down relatively quickly. If RNA was the first self-replicating molecule, it had to form in an environment where it could persist long enough to undergo natural selection. Some scientists believe that small pockets of water, such as those in volcanic rock or deep-sea hydrothermal vents, could have provided the right conditions. These environments offer both protection and a steady supply of chemical energy. If the first self-replicating molecules emerged in such environments, they would have needed a way to spread and interact with other molecules. This brings up another problem. How did early replication systems transition into more complex, cell-like structures? One idea is that simple membranes, made from naturally occurring fatty acids, formed around groups of molecules, creating protocells. These protocells could have provided a stable environment where self-replicating molecules could evolve. Over time, they may have developed into more efficient replicators, eventually leading to the first living cells. Laboratory experiments have tried to recreate aspects of this process. Scientists have designed ribozymes that can copy RNA strands and have shown that simple membranes can form spontaneously from fatty acids. While these experiments do not prove exactly how life began, they show that key steps are possible under the right conditions. Despite these advances, the paradox remains. Self-replication seems necessary for evolution, but evolution is needed to refine self-replication. The first self-replicating molecule must have arisen through natural chemical processes, yet those processes must have been precise enough to allow complex molecules to persist and improve over time. If researchers can identify a simple molecule capable of primitive self-replication, it could provide a missing link between chemistry and biology. Whether this molecule was RNA, a precursor to RNA, or a network of interacting molecules remains an open question. The challenge is finding conditions where such molecules could form, survive, and evolve into more sophisticated systems. The paradox of the self-replicating molecule highlights the difficulty of explaining life's origins. The molecules that make life possible today depend on an intricate system of interactions that seem unlikely to have appeared all at once. Understanding how simple molecules could have begun the process of replication is one of the biggest puzzles in the study of life's origins. In most species that reproduce sexually, the number of males and females is close to equal. This seems puzzling because males and females contribute differently to reproduction. Females usually invest more in offspring by carrying and caring for them, while males often compete for access to mates. Given this difference, it might seem more beneficial for a species to have more females since they directly contribute to producing the next generation. Yet, the numbers stay balanced. This is known as the paradox of gender ratios. To understand why this happens, consider what would occur if one sex outnumbered the other. Suppose there were twice as many females as males in a population. In this case, a male would have a higher chance of finding a mate and passing on his genes. Parents who had more sons would be at an advantage because their male offspring would have better reproductive success. Over time, this would lead to more males being born until the numbers evened out again. The same logic applies if males outnumber females. If there were more males, then having daughters would become more advantageous. This balancing effect keeps the ratio close to 1-to-1. The mathematician Ronald Fisher formalized this idea in the early 20th century. His argument, now called Fisher's principle, explains how natural selection favors equal investment in both sexes. The key idea is that each offspring has one mother and one father, meaning that every generation has an equal number of contributions from males and females. If one sex becomes rarer, individuals of that sex gain a reproductive advantage. This feedback loop pushes the ratio back toward balance. This principle holds true for most species, but some exceptions exist. In certain animals, such as bees, ants, and wasps, gender ratios can be highly skewed. In these species, reproductive roles differ significantly. A single queen can produce hundreds or thousands of offspring, and many of them are female workers that do not reproduce. Males exist only to mate with the queen and often die soon after. In such cases, the 1-to-1 ratio does not apply because reproductive success is not evenly shared between males and females. Other species show different strategies based on environmental conditions. Some reptiles, like alligators and turtles, have temperature-dependent sex determination. Eggs that develop in warmer conditions may produce more females, while cooler temperatures lead to more males. This means the gender ratio can shift based on climate, but natural selection still influences these changes to optimize survival. Social structures can also affect gender ratios. In species where dominant males control access to many females, like lions or elephant seals, a slight imbalance may emerge. If a few males monopolize reproduction, then fewer males are needed in the population overall. However, this does not lead to an extreme shift because natural selection still acts to maintain balance over time. In human societies, cultural factors sometimes influence birth ratios. In certain cultures, there has been a preference for male children, leading to practices that slightly alter natural gender ratios. Advances in medical technology have allowed sex selection in some cases, but long-term trends show that gender balance tends to stabilize. Even in populations where male births are slightly more common, the natural mortality rates of men and women bring the numbers closer to equilibrium. Some scientists have explored whether evolutionary pressures might push for slight deviations from the 1-to-1 ratio in humans. For example, in times of war, when many young men die in combat, there are often slightly more male births in the next generation. Some theories suggest this could be an adaptive response to rebalance the population. However, these shifts remain relatively small, and the overall trend continues toward equal numbers of males and females. Parental investment also plays a role in shaping gender ratios. In species where males contribute significantly to raising offspring, a balanced ratio is even more necessary. If both parents are needed for offspring survival, then having too many of one sex would be disadvantageous. In species where males do not contribute, there may be more flexibility, but natural selection still works to prevent extreme imbalances. The paradox of gender ratios highlights how evolutionary forces act at the population level rather than the individual level. Individual organisms do not control whether they have sons or daughters, but natural selection influences how these traits spread. Over long periods, the forces of competition and reproduction shape stable gender ratios in a way that benefits the species as a whole. Even though equal numbers of males and females may seem inefficient in some cases, the balancing effect ensures that no one sex gains a lasting advantage. If males were consistently rarer, natural selection would favor producing more of them. If females were too few, the same effect would apply in reverse. These small shifts create a self-correcting system that keeps populations stable. Gender ratios are a key part of how life sustains itself. The balance between males and females results from millions of years of natural selection, responding to the pressures of survival and reproduction. This equilibrium allows species to adapt and thrive in a changing world. The speed-accuracy tradeoff describes how making decisions quickly often leads to more mistakes, but in some cases, acting fast can actually improve performance. This idea appears in everything from sports and emergency response to scientific research and everyday life. People tend to believe that slowing down leads to better accuracy, but the relationship is not that simple. Sometimes, moving quickly helps the brain process information better or react more effectively to a situation. Imagine a firefighter responding to a burning building. If they take too long to assess the situation, flames could spread, putting more lives at risk. If they rush in without thinking, they might put themselves and others in danger. The balance between making a fast decision and making the right one is critical. The same applies to surgeons, pilots, and athletes who must act under pressure. In many cases, they don't have time to analyze every detail, so they rely on experience, training, and instinct to make rapid but effective choices. In psychology, the speed-accuracy trade-off has been studied extensively. Researchers have found that when people are asked to make decisions quickly, they tend to make more mistakes. However, the opposite is also true. When they are forced to be extremely careful, their reaction times slow down, sometimes making them miss opportunities. This balance is crucial in high-stakes environments. A quarterback in football has only a few seconds to throw the ball. If they hesitate too long, they get tackled. If they rush, they might throw an interception. Their success depends on finding the right balance between speed and accuracy. In competitive gaming, professional players must react in milliseconds. In a first-person shooter game, waiting too long to aim perfectly can mean losing the match. Instead, experienced players develop muscle memory, allowing them to react quickly and still be precise. This happens because the brain processes movement and visual information differently when a person is under time pressure. Studies show that training under speed constraints can improve reaction times while maintaining accuracy. The trade-off also appears in medical diagnostics. A radiologist examining an X-ray must decide if there is a tumor or not. If they take too long, treatment could be delayed. If they rush, they might misdiagnose the patient. Over time, experienced doctors develop a sense of pattern recognition that allows them to make faster yet accurate decisions. Their ability to scan an image quickly and still spot subtle signs of disease comes from years of practice. In manufacturing, workers assembling products on a production line must balance speed and quality. If they work too slowly, they reduce efficiency. If they move too fast, they might make errors that lead to defects. Many industries solve this by training workers to improve their accuracy while maintaining speed, often by optimizing their workflow and reducing unnecessary movements. The brain's ability to switch between fast and accurate modes is influenced by the situation. If a driver suddenly sees a child run into the street, they don't have time to calculate the best response. Their brain immediately reacts, often by slamming the brakes or swerving. This kind of reaction happens so quickly that there's little room for conscious thought. On the other hand, when filling out a tax form, rushing increases the risk of errors, and taking extra time usually leads to a better outcome. Neuroscience shows that the brain processes decisions differently depending on urgency. In slow, deliberate thinking, the brain engages in careful analysis. This is called the deliberate system, responsible for logical reasoning. In fast decision-making, the brain relies on the automatic system, which draws on instincts and learned responses. Experienced professionals in high-pressure fields develop the ability to use both systems effectively, switching between them based on the situation. Experiments show that people can train themselves to make faster decisions without losing accuracy. In a well-known study, participants were asked to identify objects on a screen as quickly as possible. Initially, when forced to go faster, they made more mistakes. However, with practice, they improved their speed without losing accuracy. This happens because the brain adapts by optimizing neural pathways, making decision-making more efficient. Athletes train this way all the time. A basketball player who spends years practicing free throws develops a nearly automatic motion. When they step up to the free throw line, they don't consciously calculate angles or force. Instead, they rely on muscle memory and instinct, which allow them to shoot quickly and accurately under pressure. This ability comes from repetition, where the brain refines motor skills to work efficiently. Military and law enforcement officers also train for rapid decision-making. In high-stress scenarios, hesitation can be dangerous. Training drills expose them to repeated situations where they must react quickly and correctly. Over time, their response times improve without reducing accuracy. This happens because their brains learn to recognize key signals faster, allowing them to act with confidence. Some researchers argue that the speed-accuracy trade-off is not a strict rule but a flexible relationship. In some cases, thinking faster actually improves accuracy. For example, a chess player who overthinks a move might second-guess themselves and make a mistake. Meanwhile, an experienced player might recognize a pattern immediately and make a correct move without hesitation. This suggests that expertise changes the way the trade-off works. Instead of a simple balance between speed and accuracy, skilled individuals develop the ability to make fast and precise choices at the same time. Technology has also changed how this trade-off plays out. In fields like finance, where stock traders make split-second decisions, algorithms help improve accuracy by processing vast amounts of data in milliseconds. AI-powered systems analyze trends, reducing the chances of human error. In aviation, pilots rely on automated systems to assist with quick decisions, improving both speed and accuracy. While the trade-off often applies, it doesn't mean slowing down always leads to better outcomes. In some situations, taking too long to decide is just as harmful as making an error. Whether in sports, medicine, emergency response, or everyday tasks, the key is training and experience. Over time, people learn to process information more efficiently, allowing them to act quickly without sacrificing precision.